them. So all of these videos are AI generated. So given this exciting progress, we can start envisioning how film production may look like in the near future. Maybe movies will be produced completely computationally using simple text prompts. So for example, we may ask ChatGPT to write a script for us like this, and then it will just generate the movie for us. Help! Maybe we can ask it to add some special effect, like a bullet time effect, and it will do it completely computationally without any real actors or cameras, just using generative AI. So the truth is that we are quite far from there, actually very far. And despite all this amazing progress, even state-of-the-art models like Sora still have weaknesses and still depict some fundamental failure cases. So for example, they may struggle to accurately simulate the physics of objects, like this object that is being pulled out of the sand here is supposed to be a rigid chair, but a model fails to simulate that. Or in this example, where the treadmill follows the person in an unrealistic motion. In cases of multiple objects, entities tend to appear and reappear spontaneously in an unrealistic fashion. And also, the costs of scaling up video models are just huge. A single instance of training a video model requires roughly 200K GPU hours, which amounts to roughly $280K. And in terms of energy consumption, just generating half a second of a video amounts to driving an average car for 4 miles. And because of all this extreme compute requirement, designing such model is reserved only to a few big players in industry. So these models are not really accessible to us. Also, if I go back to this moonshot of film production and being able to generate films completely computationally, in order to do that, we really need fine-grained controls on various aspects of the generated scene, which these models cannot provide. Something is up with the mic. Can you hear me? Now it's back? Yes? Okay. So for example, we may want to have a very fine-grained control over camera position. We may want to control the geometry of the scene, the character's identity, their position, emotion, movements. We may want to control lighting and sound and speech. All of these controls are currently are not provided by state-of-the-art video foundation models. So at Google, I had the privilege to be able to design video foundation models, but actually my research journey in the realm of video synthesis actually started from the other side of the spectrum with single video models. And what I mean by that is that we have neural networks that are overfitted and observed only a single test video. They don't know anything about the world except this single test video. And we showed in a line of works that actually single video models can unlock several exciting capabilities. So for example, you can take this busy scene here and remove all the dynamic people here except the one that you are interested in, and take a close look and see how we not only remove the people, the dynamic people, but also all the complex scene effects that are related to them. This is a video of my son riding his bikes for the first time. And I can make this video much more memorable by stylizing the background. And you can see how everything moves consistently in a geometric, consistent manner with the video. And we can also map texture not only to rigid content, but also to deformable objects, like you can see on the flower on the dress here. And I think that the main advantage of single video models is that it's their flexibility and the fact that they enable us to go way beyond just processing raw, huge pixel volumes. We can devise fundamentally new and effective video representations. So for example, in layered neural atlases, our key idea was to take an input video and decompose it into a set of unified canonical images. So as you can see here, we have two such canonical images that we call atlases. One represents the entire content of the background, and one represents the dynamic foreground object. And each position in the video is being mapped onto these images. We also estimate the visibility of the foreground versus background at each position. And this allows us to reconstruct the original video from this representation. And the key advantage of having such representation is that it allows us to reduce the daunting task of editing huge pixel volume to editing a single 2D image that we know how to do very effectively. So I can just take these images, load it up in Photoshop, edit them, and use the mapping in order to automatically and consistently, map it back to the original video with minimal effort. Okay, so just to recap, so far I've been talking about video foundation models. We talked about the huge cost, their limited accessibility and controllability, but their key advantage is their ability to learn powerful space-time priors about our dynamic world from video data. On the other side of the spectrum, we have the single video models. They only require few GPUs. They are accessible. They will allow us to gain explicit control. But their main disadvantage is that they know nothing about the world. They don't know anything except the information available in a single video. And in both Google and Weitzman, I got the chance to work on both of these models. Moving forward, I think the way to go is actually to combine the best of both worlds. So what do I mean by that? I mean that we still want to have a model that is tailored to a specific test video, and we can design it in a fine-grained manner, but also we want to fuse into it external knowledge about the world that is learned from external foundation models. And this doesn't have to be just video models. It could be an ensemble of different variety of foundation models that can provide us with motion priors, geometric priors, generative priors, and semantic priors. Okay, so my first attempt and step towards achieving this goal was in text-to-live, where we introduced the first method that can perform text-driven editing on real-world videos. And the key idea there was to use a pre-trained neural atlas representation, sort of like a video render. So this, I remind you, this neural atlas representation is being tailored and overfitted to a specific test video. And now our key idea was to replace those manual edits that I showed you with text-driven edits. And in order to achieve that, we combined this representation with the external priors learned by CLIP. And this was way before like the big generative AI revolution. And again, we were able to achieve quite impressive results in performing those localized and semantic editing of real-world videos using a very weak prior, again, generative prior like CLIP. Okay, so one of the main challenges in pursuing my goal of combining these two ends of the spectrum is the fact that current foundation models are mostly still treated as black boxes. We do not exactly know what priors they encode and how they're internally represented. And in order to be able to fuse them into video representation, we must gain this knowledge. So we must gain understanding that will allow us to really distill those learned priors. So actually, in the time that I have left in this talk, I would like to talk about the line of works that is actually taking substantial step towards achieving that and towards diving deep into large-scale models and understanding better their internal representation. And if we can do that, we can develop lightweight methodologies that require very little compute without any training or fine-tuning. Okay, so in text-to-live, we use CLIP, and again, CLIP is not a generative model. And then came text-to-image diffusion models. and really blew my mind away when I saw those amazing capabilities to generate images that depict very complex visual signals, like composition and pose, interaction, structure, and many more. And this means, as evident by those image generation results, that these models encode these priors. So I was really intrigued by how can we take text-to-image models way beyond what they are meant to do, way beyond just generating images from text. And in my lab, we worked towards achieving this goal. So we had a line of works that expanded the capabilities of text-to-image models to provide users with more spatial control. So for example, in plug and play, we can preserve the semantic layout of a given image while still conveying the edit with high fidelity according to the text. In multi-diffusion, we expanded text-to-image generation to generate images at arbitrary aspect ratios and also to incorporate region-based text prompts. And more in the context of videos, I was very excited about how can we use text-to-image priors for video analysis, for video synthesis tasks. So in Synthscape, we showed that you can use a text-to-image model to generate 3D consistent walkthroughs in scenes. And in TokenFlow, text-to-image model was used to generate to edit dynamic content in real-world videos using simple text prompts, as you can see in these examples. And you know, the entire world is building upon text-to-image models. I think what's unique about all these line of works is that in all these cases, we use a fixed text-to-image model without any fine-tuning or adaptation or without any additional data. And this is following my agenda of once we have a better understanding of what's going on inside those models, once we understand their priors, we can build on top of that very lightweight methodologies that require no adaptation. So I'd like to now dive a bit more into technical details and tell you a bit more about TokenFlow that was presented in iClear recently. Okay, so in TokenFlow, again, our goal was to perform consistent editing of real-world videos using simple text prompt. And we started off with this very naive baseline of just editing each frame independently. We applied plug and play, for example, on each frame independently. And you can see that the consistency just breaks in this naive baseline. It's not just high-frequency flickeriness. The content really changes from frame to frame. And indeed, there is no reason to think that the content would be consistent. But we wanted to dive in and to understand how these inconsistencies are being represented inside the model. Okay, so we basically analyzed the diffusion features of the text-to-image model across different frames. In order to do that, we can take our input frames, apply DDM inversion, and invert them into the pre-trained text-to-image model, and extract some intermediate features. We focused on features from the self-attention module. So what you're going to see next is the PCA reduction of those tokens or those diffusion features across different levels of the unit. And what we can observe is that the features exhibit this shared and consistent representation across different frames. So the RGB is consistent and the features depict similar consistency in the internal representation of the text-to-image model. So to gain a bit more fine-grained understanding of this internal representation, we did some simple analysis where we just took one feature and computed its nearest neighbor field to other frames. And we saw that those correspondences are semantic and accurate, as you can see in the locations in the RGB space here. And you can compute this nearest neighbor field densely, which we defined as token flow. So each token is being associated with its nearest neighbor in another frame, and that gives rise to this flow field that we named token flow. Okay, so now what happens when we apply the per frame naive editing? Once we do that, we can see that the consistency of the features breaks as well. So there is a tight connection between consistency in RGB space and consistency in the diffusion space. So our key idea in this work is to develop a framework that can achieve consistent features during the editing. If we can achieve that, then it will be reflected as RGB consistency. And the way to achieve that is basically by enforcing the original correspondences between features, the original token flow field on the edited video during the generation process of the edited video. And just in a very high-level explanation, our framework is composed of two main stages. So first, we take our original video, we apply DDM inversion, as I explained, we extract the tokens and compute the token flow, this dense nearest neighbor field between the features. And then during the editing sampling process of the edited video, what we do, we iterate between two stages. In the first stage, we sample some keyframes and jointly edit them using extended attention. This gives us sort of like a global consistency between the content that is being generated. And then we extract the tokens from these edited keyframes and propagate them to the rest of the frames using the original token flow that was computed on the original frames. And repeat this process. So by enforcing the original correspondences between features on the edited videos, we can achieve very nice consistency in RGB space, as you can see here. Again, and this is achieved with a pre-trained and fixed text-to-image model without any adaptations. And this is just to show some comparisons to existing methods at that time. So TuneVideo is fine-tuning the inflating the text-to-image model on a single video. And Gen 1 actually operates by conditioning on depth maps. And you can see that our consistency is much higher. Okay, so this was all very exciting, but again, we are dealing with videos, and in order to deal with videos, we must go beyond just 2D priors, right? Like text-to-image models can only provide us with 2D knowledge, and they do not provide us with motion priors. They cannot give us this information about the tendency of how objects tend to move in the world. And if we really want to model our dynamic world, we must incorporate such knowledge. And that brings me to the last work that I want to present today, which is actually presented here at CVPR. And again, in order to do that, I remind you that we now have much, much better capability in generating videos. And even if these models are still not perfect in the way they can simulate the real world, they can still provide us with very valuable priors about our dynamic world. Okay, so in space-time features for text-driven motion transfer, again, it is presented at CVPR. Our motivation was, again, film industry, which often involves a lot of manual work and special capture in order to create the CGI effects. Like actors needs to wear those motion markers, and then there is a lot of work by professionals that is being done in order to transfer the motion to a new object. So we wanted to achieve the same result, just completely computationally. So the input is a driving video, as you can see here. And using some simple text prompt, we can transfer the motion of the original object onto new object categories. And from just observing these examples, you can see that what is required here is not pixel level motion preservation. We want to allow objects to change their shape in order to convey the new object category, right? We need to somehow distill the essence of motion from the dog and being able to generate plausible, realistic horse, which, drastically different in terms of shape and fine-grained motion characteristics. And in order to do that, we must incorporate some prior knowledge about how things are moving in the world. So in order to do that, we used a pre-trained and fixed text-to-video model, in this case, ZeroScope. You can see some sample results by this model. And again, this model is really far from state-of-the-art, but still can provide us with valuable information about the world. And again, in the context of this work, the way we define motion is not pixel-level correspondences, but rather a sequence of semantic object part positions. We treat the object as, you can think about the object as a collection of parts and their positions, and we want to maintain that under the edit. And prior work is really not designed to deviate in structure, is more designed to, again, preserve pixel-level motion in real-world videos. So here, too, we took the same approach of diving inside the video model and understanding how space-time information is internally encoded in the model. Again, we can do that by applying DDIM inversion on a given video, fitting it into the diffusion model, and extracting features. In this case, because it's a video model, our features are F by M by N by D dimensions. So F is the number of frames, M by N are the spatial dimensions, and D is the number of channels. And here, in order to gain a better understanding of these features, we adopted this approach of feature inversion that was originally suggested in the context of understanding classifiers. And very briefly, just to say, we have some pre-trained model, fixed model, and we fit some input into this model, extract some features, and now the goal is to optimize for the inputs such that when we'll fit it inside this pre-trained model, we will be able to get the same internal representation. So in our case, we took this video of a woman performing jumping jacks. We extracted the features, and now our goal is to optimize for a new video such that when we'll fit it in the neural network, we will be able to match those space-time features. And this is being done by optimizing XT, the latent, the noisy latent at each diffusion time step. I won't go into the technical details, but this is basically just using guidance. So here you can see the feature inversion results across different seeds if we apply this optimization from different seeds. And you can see that just having these constraints of matching the features gives a nearly a very accurate reconstruction results with respect to the original video, which is not good for our task, because I remind you that we want to allow this flexibility and this ability to deviate in structure. Okay, so we want to be able, again, to maintain the general pose of the object and location, but at the same time be robust to appearance changes and shape and the exact shape configuration of the object. So our goal was to reduce the pixel level dependencies from those features. And the way we achieve this is by collapsing the spatial dimensions of the features. So for each frame, we have M by N by D feature, and we just apply averaging on the spatial dimension where each frame is being represented by a D-dimensional feature, as you can see here. And we call this feature spatial marginal mean, or SMM features. And now we can repeat the same inversion experiment as I showed you, but now matching the SMM features and not the full space-time features. And if we do that, we can see that we gain much more flexibility in terms of appearance and even the global position of the object in the scene. But surprisingly, we are able to preserve the pose and to quite high accuracy, even by collapsing the spatial dimension. This was actually quite surprising when we discovered this. But again, you need to think about these features that they live in this really high dimensional space. And this information seems to be preserved even after this averaging. Okay, so now that we have this descriptor, we have the SMM features and it acts as a descriptor of motion, let's use it for editing. So the way we do this is we take the original video, extract those SMM features from the original videos, and then use them as guidance during editing. And again, this is done using classifier guidance. We sample from the diffusion model using our target text prompt. And at the same time, we want to optimize for XT such that the SMM features of the edited video would match those of the original video. And if we do that, this is the result we get. So a camel that is squished into the shape of the elephant. So not quite there. It's in the direction, but not quite there. So in order to even allow more flexibilities in the features, instead of matching or instead of using the SMM features directly, what we do is we compute an F by F matrix where each entry in this matrix is just the difference, encodes the difference between two SMM features. So essentially, we want to preserve the pairwise differences between the features and not the features themselves. And again, during editing, we will sample from the diffusion model with the target prompt, and we will optimize XT to match those pairwise differences in the SMM features. And now we can get what we want. We can get a nice looking camel moving in sync with the elephant. Here are some more examples. And again, I think it's really nice to see, again, the role of the video prior here. Again, it needs to create those bunny ears and move them in a realistic manner. This cannot be achieved without a prior about how things are moving in the real world. Yes, more examples. Again, very drastic changes in structure across those different categories. And again, compared to existing methods, including ours, token flow, these methods are not designed to allow this deviation in structure as our method is. Very briefly, we wanted to also contribute a bit in terms of how to evaluate these models. So there is no, in order to measure fidelity to the text, you can always use clip score, but we wanted to measure how well we capture the motion, how well we preserve the motion. And again, because we are not preserving pixel-wise correspondences, we wanted to evaluate motion similarity in a more flexible manner. So we consider, we proposed a metric that measures basically the similarity between two sets of unaligned trajectories. So we have the original video, we can apply off-the-shelf tracking method, get the set of trajectory. We can do the same for the edited video. And now we have two sets of trajectories that we want to measure their similarity. And we basically propose to use something like the chamfer distance, measuring the correlation between each trajectory in one group to its nearest trajectory in the other group. And here are the results. So here you can see the motion fidelity score versus the clip text similarity score with some baselines. So basically you want to be on the top right here, right? Like you want to have high motion fidelity score, but also clip text similarity score, which will convey the edit. And our method provides the best trade-off between these two requirements. You can see that methods like token flow that preserve the motion in a pixel level manner, they get higher motion fidelity score, but lower clip similarity score. And SD edit with little noise level, again, maintain the original motion, but cannot fulfill the edit, while with high noise, it's the opposite. It can maintain the edit, but deviate significantly from the original motion. There are some limitations that basically comes from the fact that, we are also bounded to what the video model learns about the world. So it cannot transfer the motion of this woman here into a squirrel. It doesn't know how to synthesize a squirrel in this pose. So we are bounded by the quality and the priors given to us by the video model. Okay, so just to summarize, I guess I showed you the two ends of the spectrums. We talked about video foundation models there, and on the other side of the spectrum, single video models. We talked about the pros and cons. I hope I managed to convince you that there is a lot to be done and unlocked potential in this approach of combining the best of both worlds. I think we are really early on in this, in achieving this goal. There is a lot to be done, to devise this new effective smart video representation that will take us beyond pixel volume representations. We need to understand the priors embedded in video foundation models, and we need to think about clever ways of fusing them. I'd like to thank my students and collaborators on this project, and also collaborators from Google, and to thank you and the organizers. And I'll continue to work towards breaking new ground in video analysis and synthesis, and hopefully achieve at some point this goal of creating these really professional effects using simple text prompts and using intuitive methods. Thank you.
Questions? At the back, hi, please shout.
Thanks for the amazing talk. So I'm just wondering, do you have any insights that the knowledge encoded in the spatial temporal features of video photo can be leveraged for like other distributive tasks, like action recognition or something like that? Because like in text-to-image diffusion features has been widely used in a lot of like distributive tasks, like yes. Correspondence and
yeah.
Text recognition.
This is an excellent question, and actually direction that we are working on in the lab. I think there is a lot to do with space-time features beyond just video editing tasks, also analysis and discriminative tasks, as you said. I think we don't know almost nothing about the internal representation of video foundation model. Yeah.
There was a question here. Hi.
Yeah. Awesome.
Thank you.
I was wondering if you could talk a little bit about the way you would curate these single videos. I mean, that's an amazing technique, and I just couldn't even imagine how to curate.
I mean, you can think about it as NERF, right? Like in NERF, you overfit in a set of neural networks into a given 3D scene. So you can think about single video models as analogy to NERF, only not going necessarily through full 4D reconstruction of the scene. So, but you do use neural network to parameterize the information that you have in that video in an effective way that can unlock new capabilities. I hope I answered the question.
Let's thank speaker one more time. The PK's award, the Microsoft New Faculty Fellowship, TR35, Sloan Fellowship, SIGGRAPH, Significant New Researcher Award, and also 4 Best Paper Awards from major computer vision conferences. Let's welcome Noah.
I wonder if it's going to work. Oh, it looks like it's working. Can I also, oh, but I can't switch screens. Let me see if I can fix that really quick. How do I,
You're sharing the
That's what Zoom sees. That's not good because that's like a, yeah. Okay. Okay, I'm gonna, oh, Zoom quit. Oh, it's like a Zoom. Yeah. Has anyone ever seen Zoom crash? That's weird. I've never seen it. I don't have to have, by the way, I don't have to have presenter mode. Turn off presenter mode too. Okay. This is so cool. Well, okay, maybe I'll just ditch my live demo and I'll just present Zoom to, I think it is weirdly. Oh, maybe I'll do screen two. Now what does Zoom look? Okay, I'm gonna ditch my live demo. Sorry. Hey, it's just too complicated. Thank you so much. So it's great to see you all. Does this work? I don't know if that works. Press down. Okay. That's not working. That's okay. Oh, I'll try now. It's not working. That's fine. This is so amazing. It's great to see you. Wonderful to be here this morning. Hope you're having a good CVPR so far. I'm Noah. I'm going to talk about posing everything. And so I guess first a confession. And my confession is that I have an obsession with camera posing. There's almost nothing I love more than posing cameras. What gives me great joy is taking unstructured sets of 2D photos, like the pile of photos of the Coliseum you see on the left there, and using Colmap or whatever 3D reconstruction tool to turn them into geometry, like lift these 2D photos into 3D. Like you see these nice posed cameras here. You see the you see the nice posed cameras, you see the 3D point cloud. I just love it. I would spend all day doing this if I could. I've been doing this for many years. But I've always had this feeling at the back of my head that this is not useful. Like this is just my own pet obsession. There's no real application for this other than it's cool, like maybe a cultural heritage or VR, I don't know. But recently I've been more optimistic that there is a new application for this kind of data and a new reason to get up in the morning. And that is generative 3D. So I would love to be able, I think 3D is kind of maybe one of the frontiers of generative AI. And, I'd love to personally be able to generate like beautiful 3D models or rooms or buildings or cities or planets. I just would love to be able to generate anything at, photorealistically at every detail is right in 3D. And I feel like, okay, I think posed imagery is a scalable path to generative 3D. So, there's some work that is pointing to this direction. One of the first papers that crystallized this for me is a paper called 3Dim from Daniel Watson and others at Google a couple of years ago, where they do view synthesis using diffusion. So what you see is like input view on the top there of a chair in this case, or a toilet. I don't know why everyone uses toilets, but anyway, and you see it emerging from noise as another view. So you condition that input image on a new view you'd like, and you get, using diffusion, that viewpoint out. And then you can generate many views this way from a single view, and maybe you could fuse those into a 3D model, like here you see many views generated here. This is just very creative and cool. And of course, a recent paper that's very famously did something related is 0123, which shows that you can take stable diffusion or some image diffusion model and fine tune it on a view synthesis task. And you kind of tease out the latent 3D information that's embedded in the model. Okay, so you can then even apply it and ask, okay, for things that normally you don't think of as 3D models, like paintings or having an underlying 3D, you can ask it to generate these with the viewpoint changed by 120 degrees. Yeah, just amazing stuff. By the way, none of this is my work so far. I'll just very inspiring kinds of things. And the key is, training with a view synthesis loss. And the way that works is you take an input image. This is how 0123 works. You take an input view. You take a camera pose, relative camera orientation R and camera position T. And then you feed that into the diffusion model. And it should output this object from a new viewpoint. And you train this on lots and lots of, all you really need to train this, you don't need 3D. You just need lots and lots of images, pairs of images with known relative camera pose. And then once you can do that, again, you could take a single image, generate many views using this technology, and then fuse them like into a NeRF. Now you have many views, you can use whatever 3D reconstruction you want to generate a 3D model. So I think this is a very nice way to go, for instance, from image to 3D. But of course, I think in everything in life these days, data is key. So 0123 is trained on Objaverse data, synthetic renderings of these human modeled objects, and therefore it can't really generalize to things that are not object style scenes, like full rooms, I don't know, buildings, planets, cities, etc. More recently, so I think people have been trying to fix that. So there's been recent work. So one of them is called Zero NVS. That's a paper from Carl Sargent and his colleague, his co-authors, that will appear at CVPR, this CVPR, and they've trained it on more data. In fact, multiple data sets: Co3D, Real Estate 10K, ACID. So these are all video data sets, and therefore they can work on, I think, more general scenes. So like objects in situ, objects in context. So here's a nice 3D reconstructed motorcycle from a single image. Because it's trained on Real Estate 10K, which is home interior scenes, you can generate nice 3D rooms from a single image. It's really cool. And it benefits from training on more data. And then very recently, this paper Cat3D came out, which trains on even more data, Objaverse, MV-ImageNet, etc., and trains this multi-view diffusion model and gets really beautiful results. But I don't think we're finished yet. We need more data. So if you try something like Zero NVS on, well, it works really well on object-centric scenes, like these here, sort of like NERF 360 style scenes. But if you try it, we've tried it on kind of more general scenes, like building exteriors. And sometimes it works, and sometimes it generates sort of hallucinated results, like park benches looking things to the buildings. And I don't think this is Zero NVS's fault. It's a great method. I think it's the data's fault. We need more data. We need lots of data. We need scene level data. Okay. So this has been, I would have done this anyway because I love camera posing, but now I have a reason, maybe a good reason to justify like running, many servers with Colmap for months and months at a time. But what we want more data. We want posed cameras for every scene. And we want it to be, first of all, scene level, not just object level. We want full scenes. We want it to be large. We want it to be diverse. We want it to be open so anybody can use it. It's not, behind a paywall or restricted. We want high quality imagery. We want it to be multimodal, like most things should be these days. We want it not just to have images and poses, but also things like text and, maybe even floor plans and maps and any kind of contextual data we can get our hands on. And we want it to be, I don't think like one data set is ever going to be the end all and be all in this kind of enterprise. We want to be complementary to all the other great data sets so that people can train on everything and get just amazing results, including things like Infinigen, procedural generated scenes. There's a great recent data set of videos. Oh, it's dark here. That's very cool. Called DL3DV 10K, etc. Okay, so we did something like this. We built a data set called Megascenes. This is from Cornell, and this is led by Cornell students Joseph Tung and Jean Cho, along with a lot of other collaborators. And what we built is what's called Megascenes, but it's only 100,000, but there's no good Greek prefix for 100,000. Okay, but we built over 100,000 structure motion reconstructions from around the world. It's got many millions of images, but 2 million registered images, freely licensed, etc. And all the data is opened with permissive licenses. And this is online now. I think as of yesterday, the data set is live. And how do we build this? Well, so a big inspiration was this data set called the Google Landmarks V2 data set, which was not 3D. There's no camera poses or anything like that. It's 2D. It's for 2D instance level recognition. So retrieval, like landmark recognition kinds of tasks. And what they did is they enumerated hundreds of thousands of scenes and gathered images for all those scenes and then built a big benchmark, which really drove progress in this field. So we used the same kind of underlying data that they did. We used data from Wikipedia, in particular, Wikimedia Foundation data. Okay, so first you have to come up with a list of things you want to reconstruct. By the way, so when I say every scene, we want to reconstruct every scene, well, I really mean just every scene that Wikipedia knows about, which, okay, famous scenes, but also some not so famous ones. So there's this great resource called Wikidata. It's kind of like a sister project to Wikipedia, where it's like a knowledge graph. So it has like categories of things like tourist attractions, and then a bunch of members of that category that you can enumerate. So for instance, I don't know, some example tourist attractions that this knowledge graph Wikidata knows about are the Acropolis, the Antwerp Zoo, Berlin Cathedral, et cetera, et cetera, et cetera. Okay, for each of those categories, for each of those like instances of a thing, of a scene, you can then go to Wikimedia Commons, another sister project of Wikipedia, and you can find lots and lots of images of that thing, categorized under many subcategories. Like, okay, here's the Berlin Cathedral. You can get image of the interior of the, interior of Berlin Cathedral, etc. Okay, then with all those images, you can run 3D reconstruction, like Colmap. We found anytime you run something 100,000 times, you discover all of the problems with it. So we had to develop some technology called doppelgangers to disambiguate like repeated patterns and build things more robustly. But at the end of the day, we get a bunch of structure motion models from every scene that is known to Wikipedia. Okay, so that's what we did. Here's a few example visualizations of scenes. I would show you a live demo, but I'm very scared to change my window to Chrome. But there's a live demo online that I'll point you to in a second. Okay, but it has, it has minarets, it has wooden churches, it has sculpture type things. It has a bunch of it has a long tail of things in the world. Okay, but that long tail, the head of the tail is actually religious buildings. It's just some statistics of what's in the data set. Things like churches are very common around the world, it turns out. But a whole bunch of other things like bridges, towers, palaces, fountains, lighthouses, streets, and so on. I guess to a first approximation, this is a heavily biased data set. It's like a European landmarks data set because that's like Wikipedia is biased towards Europe, but it does have kind of coverage on many, many continents as well. Well, there's only 7 continents in the world, I guess most of the continents. Okay, and like I said, if you want to see a web demo, it's really cool actually. You can it does autocomplete. You start typing in a landmark and it will show you all the landmarks with that substring. Check it out. It's really cool. Okay, so now we have like posed images. We have lots and lots of posed images. So we can use this to do what I was talking about earlier. We can train view synthesis on this data. Okay, so in particular, here's one reconstructed landmark. You can just sample pairs of images from it, like these 2 images, looks kind of like Andrew Carnegie. Or you can sample some other pair of images. And then instead of running your 0NVS training or 0123 training on synthetic data, you can swap in your nice real images of scenes and just train or fine tune one of these models on real posed images. Just one caveat is though, I don't know yet how to handle the fact that if you just sample 2 random images from the internet of a landmark, there'll be different illuminations, like one will be sunny and one will be, nighttime. So that's okay because this data set is so big that there's lots of data, even if you restrict it to photos taken by the same photographer, because if someone uploads something to Wikipedia, who their identity is known, anonymously, I guess. But you can find images taken by the same person within 3 hours, and limit your training to relatively fixed illumination. So we did that, and that still yields millions of pairs of images. And then you can fine tune things like 0NVS on these pairs. Okay, and what you get is something like this. Those are just some example fixed illumination pairs. Okay, so I'm going to show you some results here. Now, I should say, if you're used to Sora, I'm not going to show you Sora quality things. We're very scrappy. This is a Cornell project. We don't have a million GPUs. But let me tell you how we evaluate this. So here's an example pair of images that aren't known to the model during training. Actually, this whole scene is not known to the model during training. Here's the model. Here's the image we're going to feed to the system. And here's the ground truth view, which is unknown to the system. Okay, if you take something like 0NVS, because it really hasn't been trained on data like this, it does, this should resemble the target image, but the kind of interpretation of pose, it's not quite getting it right. If all you do is fine tune 0NVS on megascenes, you get much more, you get a result that much better kind of matches the pose of this target image. Because this is a generative task, it has to make up a lot of this building. Of course, they won't match exactly, but the viewpoint at least should match, and sort of the gestalt of it should match. Now, there's another thing you can do. All these models that I've been talking about condition on numbers that represent camera poses, which is kind of a weird thing to do, to feed like 12 numbers in a projection matrix to a model. It has to interpret this. So I think there's a much stronger form of conditioning that you can give to these models, which is earlier work like Infinite Nature did something like this. You feed in you take the input image, you predict depth, and then you warp it to the target viewpoint. Okay, so you warp so basically the pixels you know about from the input view, you can approximately get them right just by warping them to the output view with predicted depth. Okay, but then you can also use this as conditioning to your view synthesis model. And now, instead of just interpreting the numbers as a pose, it gets to see the effect of that pose on some known points, which is I think a stronger kind of conditioning for viewpoint. Now, one simple thing you can do is just do stable diffusion inpainting on this warp condition image. It doesn't work very well. It tends to make up picture frames and stuff. But if you then condition 0 and VS on this additional warp condition signal, now this is the thing that kind of works better than anything else. Okay, again, it's not matching this target image exactly because it's a generative task, but it's getting a more kind of realistic view of this scene. Okay, here's just some more results. Maybe look at this bottom one as an example. This is where 0 NVS is kind of having a lot of trouble interpreting the pose, but where fine-tuning on the megascenes data gives much more kind of consistent results with the actual desired pose. You can kind of see the visualization of the target pose here. Again, this is not to say 0 NVS is bad. I think, and by the way, I'm showing images here, not synthesized NeRF models from SDS losses. These are just raw images. But it's just training on more data and giving it more ways to better ways to interpret pose is helpful. Okay, you can use this to synthesize views along a viewpoint. So here's warped images along desired camera trajectory. Here's what you get if you just run per frame 0 NVS. Again, it's having trouble interpreting the pose. If you fine tune on megascenes, again, this is just per frame completion of this work, per frame view synthesis. So if you fine tune on megascenes, it's still very jittery, but it's doing a better job. If you also give this warp conditioning, it's much more consistent. Again, this is not like a Sora quality video. We're just doing per frame. There's no video diffusion model or anything under the hood. It's just doing per frame view synthesis. We get kind of much more consistent results. Here's another example where you see that, again, fine tuning and warp conditioning lead to better results. It turns out that if you fine tune on megascenes, it also works better on other data, like real estate 10K. Maybe because it's seen more examples of poses or more rich examples of poses, that is helpful. I don't know quite why, but it seems to work better on real estate 10K. Again, you can see our results, the fine tune and with warp conditioning on this column, which perform better than the other methods we tried. A couple other example results. It gets this picture frame kind of nicely generated. Okay, so one thing I really like about data is when it comes with extra goodies. So like I said, this megascenes, because it comes from Wikimedia Commons, it inherits all of the kind of metadata that comes with Wikimedia Commons. So it I'm not going to go into this in too much detail, but if you could spend a lifetime drilling down on details of Wikimedia Commons. There's a category for Notre Dame Cathedral. That's not surprising, but you can find historical photos of Notre Dame Cathedral. There's all these subcategories of Notre Dame Cathedral, I don't know, love padlocks at the Notre Dame Cathedral. There's a whole set of images of that. There's a category for the great organ of Notre Dame Cathedral. There's actually several organs, multiple organs. There's a category for just this one. There's this weird subcategory called chamades of the great organ of Notre Dame. The chamade, it turns out, is a organ pipe that sticks out horizontally instead of vertically. Anyway, there's all this rich data. There's captions on images. And by the way, this Wikiscenes is very much built on a previous work we did led by Hadar Alor and Xiaoshi Wu, a project called Megascenes from a couple years ago. Okay, so it's very rich. Now, I want to talk very briefly about another source of posed images with rich context, and that is Street View. Okay, so Street View cars are whizzing around the world all the time, collecting images. These images have sensor data like GPS and IMU, and so you have captures around the world with posed images from this metadata. So for any point in the world, like this Street View image in Seattle, It exists in like the context of the entire world. It knows like what street it's on, what the buildings around it are. It knows the roadmap around it, and it knows the ratings of the restaurant across the street. Who knows? It knows everything that is known from map data about the world. Okay, and so in recent work that will appear at SIGGRAPH, this is work from Google, led by an intern, Boyang Deng from Stanford. This work is called Streetscapes. We tried to like leverage this data for an interesting task. So in particular, the task we perform is layout conditioned scene generation, where a scene is represented as a video or a sequence of images. So the input to the streetscape system is a map. It could be like an actual map or a made up map of some place. And it could take in a description like Barcelona as well. Okay, so which means, okay, make it look like Barcelona. And what it does is it generates not like a real street view, sequence of street view images, but an imagined generated so-called streetscape, which given a user indicated path through some trajectory through this map, it generates the imagery according to that trajectory consistent with the input map data. So the world should look like what the map tells the system it should look like. There should be buildings and green stuff and roads in the right place. Okay, so this is like a controllable video generation method that can be controlled with a layout. Okay, and the way this works is actually, so it conditions on a layout image and a height map. So it tells you, you have to tell it how tall the building should be. And this gets rendered into ground level conditioning data. So this gets rendered to, one word for this is a G buffer, or a set of G buffers, a sequence of G buffers. A G buffer is like a deep buffer. It's like a word in graphics for when you have like a buffer of multiple kinds of things that you feed to a system. In this case, the G buffer consists of a semantic layer, which is literally just the colors of this map encoding like, types of things like buildings. That gets rendered from ground level. There's a depth map and a height map that get rendered from this ground level trajectory. And then that gets fed to essentially an image diffusion model that's lifted to be a video diffusion model, and that gives you your streetscape. And just like how this technically works is something like this at a very high level. You have the sequence of camera poses that you want to render the world from. Again, this imagined, sort of generated imaginary world. The first K frames, K could be 2 or 4 or something like that. The first K frames are generated in parallel using kind of a multi-view diffusion model that are parallelly denoised from those two images G buffers. And then every subsequent frame is generated autoregressively by conditioning on the previous frame and the new frame's G buffer. And then you can generate a sequence of any length because now you're just running this model autoregressively. You can run it as long as you want to. Okay, so, and this is trained on large sequences of large triplets of things like map, camera poses, and images from street scene data from a variety of cities. Okay, so it's really leveraging that contextual data we have from maps. Okay, here's just some example results. So what you're seeing is, the map with the camera trajectory overlaid on it. You're seeing just the raw generated video here. It's not perfectly consistent. There's nothing forcing it to be perfectly consistent. Although maybe, with more training, we can make it more consistent. There's a little bit of flickering, but then you can synthesize that into like a NeRF model and have a more consistent result. Okay, but they're pretty consistent. Even just the generated video is pretty consistent. And then you can generate a bunch of, kinds of scenes, and you condition and say, oh, actually, there's not really much street view data that's like snowy scenes, but you can leverage the like image diffusion model this was conditioned, fine-tuned on to generate a richer set of scenes. Some fun things you can do are, like I said, control time of day and weather. You can make it evening or morning or rainy or snowy. You can even make Barcelona snowy, which isn't typically, known to be snowy, a snowy city. Here's some images generated of Paris from this layout. But then you can also say, okay, I want this layout. This is like a real Paris layout. This is like real Paris streets. You can say, okay, I want the Paris layout, but I want it to look like some other city. So it's like, what makes Paris look like New York City or London or Barcelona? Conditioning on a layout from one city and making it look like another city. like that old paper, What Makes Paris Look Like Paris. Okay, good. So I want to leave with a couple of, okay, there's a great word, lagniappe, that I knew a long time ago, but just remembered recently. A lagniappe is a bonus thing. It's like the 13th donut in a dozen donuts. I think this is like a New Orleans style word. So maybe if you went to New Orleans CVPR, you heard this word. Anyway, so here's just a few lagniappes that are not necessarily that related to what I talked about earlier, but I just wanted to share. Okay, this is very recent work of my Cornell student, Haiyan Jin. And the goal here is to relight images with diffusion models. So basically what we do is we take this 0, 1, 2, 3 kind of training, but instead of synthesizing new views, we say, okay, it probably knows about lighting too, in addition to 3D geometry. So let's tease out the like relighting knowledge that stable diffusion has. Okay, so we change the task to take an input image. Instead of a relative camera pose, you give it a environment map and say, it's like an HDR environment map. You say, I want the image to appear as if it was rendered by this environment map. And then the output is a relit image under that new environment map. Okay, it's just that, well, there's a lot of details to get to work, but in particular, the training data. So this is trained on image, environment map pairs rendered from a clean Objaverse data set, where the details of the cleaning and so on are in the paper. So this is an archive paper called Neural Gaffer. A gaffer is I think it's a gaffer is a person on the film crew who does lighting. So this is relighting any object with diffusion. Okay, so here's just some results. You see the input image on the left-hand side. You see the desired output images environment map on the upper column. You could also generate an environment map by running a text to HDR panorama method. And you can see the relit images in this matrix. And we have some way of, okay, the thing, I guess maybe the most interesting thing to pay attention to is not just the relighting, but how do specularities change? Like if it's shiny, how do the shiny bits move around? And we have this way of making the results consistent under like a rotating environment map. So if I rotate the environment, you see these nice kind of consistently changing single image relit results where there's kind of nice smooth changes in lighting as the environment map's rotating. So it's like the object is fixed. We're not changing the object viewpoint. It's just the entire world is rotating around it. So this is online at this Neural Gaffer page. I also want to call out another paper that just appeared very recently called Illuminerve that does that explores some related ideas in the 3D context. So it relights 3D nerfs without kind of explicit inverse rendering. Okay, and then one more lagniappe really quick is we have this paper that appears at CVPR today on not generating video, but generating motion with diffusion models, where you can take that motion and then animate a still picture with it. So, take a still image, generate a seamlessly looping video. This is work led by Jungchi Lee and Alex Zelinsky that will be later in the conference. And the idea here is, instead of predicting this big volume of RGB pixels or latent descriptions of RGB pixels, we predict a spectral volume, a spectral description of motion in the frequency domain. This is an idea from a classic paper by Ave Davis from SIGGRAPH. This representation comes from that paper. It's called a spectral volume. And this is a much more compact description of motion. Okay, and so what you can do with this is generate motion and then animate the images accordingly. And you get this works well for like oscillating things. And you can do this it also, using the same kind of Abe Davis technology, you can turn this into an image space modal basis to interactively kind of poke and pull things in an image. Okay, so I'll wrap up here. So to summarize, posed imagery, I think, is a really compelling and scalable source of supervision for 3D, beyond objects to like scenes and things. Contextual data from Wikipedia is really interesting. I just love this data. A few open challenges I'll just leave you with is, I think video diffusion models seem to be doing well at 3D. We have these kind of parallel 3D generation methods. What's the right way of combining them together? I think we're seeing a lot of interesting explorations in that vein. I think another open challenge is, we don't just want shape of things. We want full like BRDFs and lighting. We want to generate things that are rich and and that you could, there's like, you could put it in a Pixar movie. I think we're kind of far from that. And then I'm really inspired by illustrations like these. This is a beautiful illustration of Notre Dame Cathedral by a cutaway expert, Stephen BST. The kind of models we can reconstruct or generate in 3D look nothing like this. This is so semantically rich. Like it has the inside and the outside of a building all together. Like there's people milling around. What I really love is to be able to generate or reconstruct scenes at a rich level of detail and of semantic understanding as this. Like a full cathedral, I could point at something and it tells me what it is, where I can like go up to a candle and see it flickering. I think we're very far from that in kind of this 3D generative space. Okay, so thank you to all of the people who led this work, and I'll be happy to take questions. I don't know if there's time. Yeah, thank you. Sorry, I think I ended exactly on 10:10.
Yeah, thanks Noah for the great talk. So any questions from the audience? Yeah, Tim first.
Thank you. Very nice talk. Two questions is that like back in the old days, people with the normal views, we imagine a 3D geometry or depths and then camera point and shoot another image. But nowadays, like works and other works, just use the transformers, you can see the new images, normal views, without any online 3D geometry estimation. So my question, although like for they don't have like an online 3D model. My question is for like normal synthesis or even more like just 3D rendering, you really need a 3D geometry in future or transformer can take over everything?
I don't know. It's a good question. Can a transformer take over everything? I mean, so I think in the short term, yes, it will take over everything. It is taking over everything. But, the kind of world I imagine at the end where, I want to be able to generate a house and I open the door and go inside. And I want to like open up the cabinets under the kitchen, under the sink and find chemicals and like mix them together and they explode in the right way. Like there's something, I think eventually if you want to build a simulation that's interactive and lighting looks right and things behave correctly if you kick them or flip a switch, I feel like it might be hard to scale like a video model to that, to be kind of the ultimate computer graphics model that you might envision wanting to build. So I don't know, maybe it's possible, but I kind of feel like eventually we'll have to go back to generating explicit 3D, which has affordances and is lit according to physics and things like that.
Thanks. I just want to hear your thoughts. Thanks.
Any more questions? So me just a small question to follow up your talk. So you show we can nicely control lighting and also nicely control motion. What do you see like maybe a more comprehensive system where you can control the lighting, the motion, and different aspects together instead of like individual pieces?
Yeah, I think that's a great question. I mean, I think it goes back to that idea of like, I think, eventually it seems like what it needs to generate is not data, but like more like a computer game, right? So, the things that are moving in the scene maybe should be controlled by physics, which is encoded as a program or something like that. I feel like, we should look to like the computer graphics industry. People in games and movies have been doing this forever, and we should probably be starting to like adopt the kinds of practices that they're using. I don't know. I think it's the same answer as the previous question in some ways. Yeah.
Yeah. Yeah. Let's thank Noah again for the great talk.
Thank you. Thank you very much.
We'll take about a 7-minute break and resume.
How are you doing? I hope I didn't come across this
Hello, can you hear me? Okay, so this is Jin from CMU. It's my great pleasure to introduce Tim Brooks. The most important thing, the team actually graduated from CMU as an undergrad, but anyway. So Tim is a research scientist at OpenAI, where he co-leads a Sora model with Bill Peebles and an amazing team. His research focuses on large-scale generative models that can simulate the physical world. He received a PhD from Berkeley, advised by Alyosha Afros, where he invented instructive pics, among other papers. He previously worked on AI that powers Pixel phones at Google, and also the fancy video generative model at NVIDIA. Here you are. Yeah, thanks.
Yes. Awesome. I'm going to talk about Sora. It's OpenAI's video generation model. Some of its capabilities, some things I'm excited for moving forward, the process of working with artists a bit. I'll try leaving some time at the end for questions. Also, I'll be giving the same content in a talk tomorrow at the Transformers for Vision workshop, in case you're like so far in the back that you can't see anything. We're trying to figure out your schedule for tomorrow. All right, so here we go. Okay, clicker's not working. Awesome. So this video is really meaningful to me because this was when we hit the landmark of 1 minute long, 1920 by 1080. And that was kind of like the goal of the project from the get-go. And you can see Sora is able to get a lot of nuance about reflections and lighting and shadows and whatnot in this video. And even the woman, she's going to walk in front of this sign and she completely blocks it and then moves past it and the sign is still there. So it's able to handle occlusions properly. So yeah, this video I think was like really meaningful in the project, and it was really helpful in the project to have this really clear goal from the onset. Sora can also do a bunch of other styles as well. So here is a papercraft world. It kind of excels at photorealism. I think that's what it's best at, but it can do other styles as well. And it generates the entire video all in context, all at the same time. And that allows it to get consistency throughout these different cuts. So it's generating the cuts within a single generation, actually, and that way the style looks consistent. And it can also, sorry, some technical difficulties playing the video. There we go. This also enables it to have the consistent characters throughout different cuts in a video. So this is, again, a single video that's generated, but you're able to get this consistent character throughout. And this will probably be very helpful for content creation, that you can have the same character in scene cuts, but it's all part of a single generation. It's all in context. And that brings me to kind of these two uses that we're most excited for about video models that I'm primarily thinking about. And one is as a tool for artists. We've been working with a number of artists. Just a couple of days ago at Tribeca, there were some short films made with Sora that artists had made. And they've been giving us a lot of feedback about how we can make it more useful as a tool. That's been really valuable, especially around what controls and inputs they want to see. The other use that we're excited about is to simulate the world. And I think this is really exciting, and this is going to be like a longer term, harder thing to do. It's already at the point where it's useful as a tool to artists. It has a lot of improvements to be made to be more useful, but I think we're already starting to see that. But I really strongly believe that video models will get so good that they will actually simulate reality, and that will be useful in other ways. It'll be useful as a means to get intelligence from AI models, and that we can use the models as an environment to interact with, to plan, that could be useful for robotics. I think this is a longer term research direction, but a really exciting one. And if you're particularly excited about this world simulation angle, I'd love to chat about it. Now we'll talk some about the technology in Sora and kind of the framing for how we thought about developing it. So I primarily think of it from the paradigm of scale and what has succeeded for language models and how we can leverage that. in the context of video. And language models, they are generalists. It's a single model that can be useful for tons of different tasks. And one of the important parts of this is that it trains on a huge diversity of data. You train it on prose, on code, on math, on any data that you can get your hands on, and you do it without modifying or truncating or making these adaptations to the model. You just use it all and you put it in a universal representation, which is tokens. We tokenize all the text data, and that allows us to train these large models on a really diverse, broad set of data. So we do the same type of thing for video models by training on images and videos at all different resolutions and aspect ratios and durations. And this allows us to use all the bytes of information that are in that data, rather than, for example, like square cropping and resizing everything to be 256 by 256, which is pretty common in what I had done in the past. By training on data at its native size, you use all the information. Use the information about the composition, about what duration video makes sense for the particular content that's happening. You have all the high frequency details in there. And we then turn all these different sources of data into patches, and we have a different number of patches depending on the size of the particular example. We create the patches by first training a video compressor model. And so this is similar to latent diffusion models, where you train an autoencoder. It compresses the video data into lower dimensions, and that makes the task of modeling easier because now your data is smaller. So we compress in space and time, and we have this 3D latent space that we take pieces of, and those pieces are these little cubes in 3D, and that is our equivalent of a token. It's different from language models because these are continuously valued. So in language modeling, they're discrete tokens, and you have this autoregressive transformer. In our case, these are continuously valued tokens, and we train diffusion models on them. But this is a universal representation that lets us use videos that are long, that are short, the high resolution, tall, wide aspect ratio. It lets us use everything. And we just have these different sequence length examples, but we can train on all of them together, and our model results in being a generalist model as well. And a huge benefit of this is that it lets us use transformers, and transformers are really scalable. And I think if there's like one figure or result or thing from Sora that is the most exciting, this is it, because we have a base amount of compute that we train it on, and you can see that the result is pretty bad. It like kind of resembles a video and morphs around a bit, but it gets some elements right. And then with 4x compute, it gets the structure, it gets the layout of the scene right, it gets some primitive things, but it doesn't get the nuance. And once we hit 32x compute, it gets a lot of the nuance and the detail and the motion right. And what's exciting here is what's going to happen when we go to 100x, 1000x, 10,000x, a millionx. And that's why I'm so bullish on this idea that video models at some point in the future will be able to actually simulate reality, because they improve predictably with scale. And I want to talk about a few lessons I think we can take from the state of LLMs. And this might be preaching to the choir. I don't think these are particularly controversial things, but they're really important points to reinforce. And the first is to put your flops on the x-axis and your metric on the y-axis. This is like extremely important. And a lot of people are doing this in all different areas, but it still is like, if you are not yet doing this, I highly, highly recommend looking at the improvements that you're making in your models from this framework. And another part of this is that you don't just have one point. It's not about trying to make the metric better for a single compute scale, but that you need at least 2 points. Ideally a couple, and even if this is small scale, you can do this at small scale too, and then make your model smaller, make it half the size, make it a quarter the size, and see what the trend line looks like. And really starting to look at this from this angle of compute eventually will increase, regardless of where you are. Over time, we have better GPUs, we have maybe more GPUs, compute will increase, and we need to be looking for models and training paradigms and data sets that improve as we increase the amount of compute. The other is that evals are extremely important. They're a big bottleneck in the progress for content generation, for visual generation. It's also a bottleneck. It's really hard for language models too. But I don't think that we put enough emphasis on evals. Actually, if you're working on video evals, like, please let me know. I'd love to try them out. I also would love to like feature them in talks because I think we need to give more credit to people working on evals. It's a really challenging thing to do, but it will push the field forward. If we have evals that are reliable that we can all use, that I think will push things forward much more than advancements without the evals. And another is in thinking about how to adapt models for different tasks. And in language models, you train your base GPT model or whatever it is, and then you have these post-training that happens where you do supervised fine-tuning or you do reinforcement learning, and you're adapting the model to do a bunch of different tasks. But that adaptation is done via data. And I think this is also a really important lesson to take in for content creation as well, that the best way to adapt models to do specific tasks is through data rather than through architectural changes. And it can be tempting to like bake in some change and be like, I want to be able to adapt the style of something, or, you know, swap some objects or something about 3D. So I'm going to bake in some explicit inductive bias that seems to make a lot of sense for that task. But that's really hard to scale across lots of tasks. And what we want is to eventually get to these visual models that can do any visual generation task, that they're generalists, just like how GPT models can kind of do any type of language modeling task. And for that to work well, it's best to think of these adaptations as data that we can train on. All right, so here I'm going to talk through quickly some capabilities of Sora. So when we train on videos of different aspect ratios, we can generate videos about different aspect ratios. That's kind of obvious. Something that's a little less obvious, but also the case, is that you actually have better composition. And this is because if you're always square cropping, you're losing information about the composition of where the subject should be in the frame, and you're going to cut it off. And you can see on the right, or sorry, on the left is when we trained a model where we did square cropping, and it puts the subject off to the side, and it actually gets cropped off the side. But then when we train on native aspect ratios, even when we generate only at square, it has better composition. It puts the subject in the center of the frame because it knows that if it is square, the subject should be in the middle. Sora can also generate images. Images are a great source of data and knowledge about the world. Images are just a special case of videos where it's a video that's 1 frame long. And these are up to 2000 by 2000 resolution. And this is similar to in videos, we can use a different number of patches to train and to generate at different resolutions. I won't talk much about this one, but in order to create that training data, we train captioners, and we train these really descriptive captioners that caption images and videos, and that's how we get the text pairing to do text to video or text to image generation. And we can prompt the model in a variety of ways. We're still kind of experimenting with this, and working with artists has been really valuable to get a sense for how they want to use the model. But this is a DALL-E generated image that is input, and then it animates that image. And you can condition on an image or prompt with an image and have that be anywhere in the output video. So here, the image that we're prompting on, we put in the center. And it generates the video before and after. And you can extend videos. So most of the videos that I showed, they were all generated at once at the same time, but you also have the ability to generate a part of a video and then extend it forward or backward in time. So here I generated a video and then I extended it backward in time of this like trolley car floating through the air. But you'll see that they all end the same way. I think there are a lot of ways we can use these models, and we're only kind of scratching the surface of their uses. This is using SD-Edit, which is a great technique for modifying images, and we can use it also to zero-shot edit videos. One thing that is particularly cool here is you can see the instruction for editing it, change the video to a medieval theme in the bottom right, that the model actually like really has some intelligence there, that it makes a horse pulling a carriage. So it's not just changing the high frequency details, but there's like intelligence understanding the context of a medieval theme that then changes it to no longer be a car. And the model can interpolate between videos. So here the video in the middle starts with the video on the left and ends with the video on the right. It's a kind of cool application. I'll show a couple. I think something interesting about this is how it finds a way to make a feasible path between the two videos, and then it's different depending on the context. So in this case, like the changing the to coral is really gradual, whereas the butterfly is more abrupt. And in this case, it actually uses its understanding of 3D and of occlusion to figure out a path to conceivably get from one video to the other, where the gingerbread world is like hidden behind this castle or building, and the camera moves through space to reveal it. All right, now I'm going to talk a little bit about the emerging simulation capabilities. And I think these are pretty early stage, but this to me is kind of like in the early days of language models, we saw that they were able to get like grammar right, or they were able to get the sentence of structures or paragraphs right. So this is like early signs of understanding intelligence and being able to accurately simulate the data that you're trained on. And so the first is 3D consistency. SOAR is not trained with any 3D inductive biases, so there's no like ray consistency baked into it or explicit renderer or something, but it's able to move through space and get many aspects of 3D right. And this is, here I'm showing a SOAR generated video on the left, and then Ben Mildenhall took that and ran it through NERF. And that's kind of a nice evaluation to show it's not just tricking us. It's not just that it looks like there's good 3D. Actually, like if you then take this video and you pass it into an explicit 3D algorithm, it does reconstruct. So that's a nice evaluation. Object permanence. So this cute Dalmatian, you'll see a bunch of people are going to walk in front of it, and it still exists. The same Dalmatian even after. And this is actually was like really hard to get to work, but it's showing that it understands things about the world, that objects don't just suddenly disappear or change, even if they're hidden from view temporarily. Another is consistent entities over different cuts. I showed some examples of this earlier too, but here there are a bunch of different scenes, and this robot keeps the same kind of look throughout them. And another one that I don't actually have a specific slide for, but I think is really exciting is like actually modeling behavior of people and of agents, which, yeah, that is hard to do, and it's probably not something that they quite can do accurately yet, but I do think at some point they will get really good at modeling like interaction between people or a person doing a task and how that person behaves and acts. And this is one that's really challenging, interacting with the world and actually updating the state of the world. So here's a video where someone's painting, and the impressive thing here is that the paint stays on the canvas. And earlier on, when working on video generation at smaller scales and before things were working really well, it would do the brush stroke, but you wouldn't see any paint stay on. And here's one of someone taking a bite of a hamburger. And there's actually a bite mark. So this is pretty hard, but I think it's really important when we're thinking about simulating the world, actually being able to interact with it and update the state of the world. That's hard for the models. It kind of requires some intelligence that's deeper than just motion, right? And when we first were working on video generation, I think in early days of video generation, everyone's talking about motion, but there are these more complex aspects of the physical world that these models need to understand. And I think that over time, as we scale them, they'll get better and better. And other ones that we're not just limited to the physical world that we live in. So here's like Minecraft. And this is just the prompt, Minecraft with the most gorgeous high-res 8K texture pack ever. And And it's able to make a pretty reasonable environment and like an agent moving around in it. And, you know, it's all just a single generation, but I think we probably could simulate many different environments, not just physical ones, but, you know, any visual environment that you can create, you probably could train a video model to simulate. So Sora is really far from perfect. It has a lot of issues still. Some are with pretty basic things. Here you can see that candles are blowing in different directions. So that doesn't really make sense. She tries to blow out a candle, but it doesn't have any impact. It doesn't actually blow it out. Here's another one with a chair that archaeologists are removing from the earth, and the chair like looks kind of possessed. Yeah, so there's definitely a lot of improvement to be made, but I'm really excited about the trajectory that we're on, and I think that over time, that these things will resolve with scale, and as we make architectures and models that are better and better at just the task of modeling data. And lastly, really quickly on working with artists, it's been really amazing. Most of the work that I've focused on is the accuracy of individual clips, but artists are telling these amazing stories, and that's been really fun to see. I really like this quote from Shy Kids we worked with. As great as Sora is at generating things that appear real, what excites us is its ability to make things that are totally surreal. And I think that's cool too. It's hard to know exactly what use cases there will be for these models, and it's easy to think of things like, oh, stock footage, oh, like making a film or helping edit films, because those are applications that currently exist. But I bet, similar to how language models, people are starting to use them in ways that we never thought about 5 years ago. I bet that, you know, in a few years or in 5 years, people will be using video generation models to do tasks and to create experiences that right now we're not thinking about at all. And I'd like to show a video that Shy Kids, they're an art collective, made using content from Sora. They also edited it afterwards in other software, but all the source footage is from Sora. And I'll just have this on the background, and I'd be happy to take some questions while it's going.
Okay, let's start over here. Thanks.
Am I correct in assuming that there is no special emphasis on physics, like being correct or 3D consistency? It's just the scale of the architecture and the data that allows us these wonderful videos.
Yeah, so the question was if there's anything special about 3D or physics, or if it's just about scale and architecture. Yeah, and I mean, I would say not just scale and architecture, but it's about modeling the data well, and like having physics right, having 3D consistency right gives you a lower loss. So, and yeah, scale and architecture help get the lower loss, but the task is just like model your data really well. And if you do it really well, then physics will come as an emergent property.
In the back.
Two questions. One is, first of all, great talk. Love it. One thing is, you talked in few places that it was very difficult to get it, especially when you talked about it. How much of this is about scaling, getting data, of course, having the proper infrastructure to scale properly is very important. But how much of it are other parts, like way that you import your data into the beginning? Like how much of it lies in the scale and compute data, and how much of it was like having to actually dig deeper to figure out where the failures are coming? The second question I have is, where does video generation fit in this whole race to AGI?
Great questions. So the first question was, when I talk about how it's challenging to get certain parts to work, like what does that actually mean? Is that just scale, or is it other aspects? And it's hard to get scaling to work, is the answer. So yes, if you scale things well, and if it does your task of generative modeling well, then it's just scale. But it's not a matter of like, oh, just take your model and, train it on more GPUs and that's it. It really is this paradigm of having flops on the x-axis, having your metric on the y-axis, doing lots of experiments and studies and trying to figure out which training recipe and which architecture is going to get you good scaling properties so that when you train on the 4x compute or you train on the 32x compute, you have confidence that the model is going to be predictably much better than the previous one. And that's what's really challenging. And that's kind of the work in it, is getting the scaling to actually give you predictably better results. And the second question was how this fits into AGI. I do think it's an important step in the path to AGI because there's a lot of intelligence that isn't captured in text, just about the physical world, about how the world works, about how we can interact with the world, and having models that really deeply understand and actually can simulate that world, similar to how we can think. I mean, it's not the exact same, but we can think in our head about, I want to do something, let me kind of envision what that would be like or plan it out or try seeing what some different options would be like in our head. I think that having models that can actually simulate and roll out and try trajectories in the world will be really valuable.
In the yellow hat.
Hi, I'd like to ask about, and you can answer as much as you can answer, but I'd be curious about how do you see particularly Sora and moving forward with other video models? How much will be shared back to the research community? And how much, because your presentation is great, but all of there, of course, is what has been shared publicly. And of course, a lot of this, like, getting better. And I'd be curious about what can be shared and if you envision in the future it getting less and less shared with the community or more and more. So I'd like to hear from your perspective as a researcher in academic conference about this balance between what is shared and what is proprietary in this different scenario.
Yeah, that's a great question. So the question was what information can be shared and how maybe that will change over time for being able to share with academic communities about the research being done for these large proprietary industry models. I don't entirely know, but it is something that, like, I care about engaging in talking about what I can about these, but it's always like some level of deliberation about what the right amount of information to share is. And like getting, for example, that like technical report on Sora out that like actually does talk a lot about what the key elements to things are and kind of what our thinking about it is as a research problem. And many of these key things like training on data of all different sizes and aspect ratios and how we turn data into these tokens, at least at a high level. I like really wanted to get that information out there. And I think that it's great that we did through that technical report. Then there are also like exact details about like the config or something is like not something that we're able to, or that makes sense right now to be sharing. I don't know exactly how that will evolve over time, but I think that it will probably always be like a conversation. And we do want the field as a whole to progress and to contribute to that. But then also there are some aspects that are like proprietary that are valuable to the company that we're not going to share. So it's a tricky balance, but I think it'll evolve.
Okay, we'll do two more.
Yeah, I wonder if you could talk about your philosophy on debugging. So as you were developing this model and you saw a bad result, could be you didn't have enough data covering that, could be you just needed more compute, could be you need more parameters, could be an architecture change. Like, how did you figure out which of those you need to go attack first?
Yeah, debugging is pretty hard for it, and the lack of good evals, I think, makes debugging much harder. I think that it is like, again, going back to this, looking at it from a scaling property. If there's some thing about it that's not improving with scale, or if like your metric is not improving with scale, then there's clearly an issue. If things are improving with scale, it might be that it's just a matter of scaling more. But then if there's something that's like, it's just not working at all, that's kind of like an indication that there's some more fundamental issue. And debugging that can be challenging, but you sort of need to like dig a bit into the exact objective that you have, or maybe try like making things more toy. Like, what if I do even lower resolution or smaller? Can I reduce this to like the simplest example of this problem that I'm observing to be able to study it more in isolation? But it's very challenging to debug these. And, there were many times that I got caught on bugs that were hard to find.
Great talk. Thank you very much. I have a question about using solar as a world simulator. I guess to use solar as a world simulator, it's very important for us to understand physics in the sense of like gravity, collision, kinetics, right? So I guess my question is, if we are following your philosophy of if you want to adapt it to to learn more about physics, then it's more about data than architecture. Then do you see this understanding of this intuitive physics naturally emerge with larger model and longer training, or we do need specific data, for example, like a bunch of billiard tables, all the balls colliding with each other? What is the best way to do it? Thank you.
Yeah, great question. So I guess to summarize the question, if we need specific data for specific like properties of physics, or if everything will just emerge, I think we need evals is the real thing there. And do we need like, tons of videos of billiards to be able to do billiards? I kind of doubt it. But the way to find out is to have like an eval that measures that and to see and to look at it empirically. And we scale the model and we see if it's getting better at this. And my guess is that it will just get better at that without particular attention. But maybe there will be some areas where we do need particular data sets for them. And we really just need to have like a robust evaluation framework to see which areas are data limited or which are scale limited. Awesome. Thank you all so much.
Hi, Dee. Can you hear us okay?
Hi, can you hear me?
Okay, I'm just going to set up a laptop for you.
Okay, great.
Dee, would you like to try screen sharing?
Yes. Can you see my screen?
Okay, and then the next question is we have to somehow get the audio to work.
Can you hear me?
You want to try it?
Okay.
We're going to try and what we're going to try and do is point the microphone at this.
Okay.
The room speaker. Okay. Can you try speaking for us, please?
Test.
Okay, hold on. We can't hear you. Just a second. Okay, let's try that again.
Test.
Okay, great.
Great. Can you see my slides just with the screen?
Yeah, we can see your slides as well. All right, everybody, our next speaker is ready, so please come and take your seats.
We need to mute ourselves.
Because it needs to come out here. So I get it. All right, let's let's test this. Can you just say a few things and we'll see if we can hear you in the room. Can you go ahead?
Hello from Mexico City.
Oh, wow. I have this as loud as I can. We're going to have to try to test this a little bit more. Can you just say it, and I'll see if people in the audience can hear. People in the audience, hello. Can you give me like a thumbs up if you can hear something?
Hello, hello. Hi.
It's very loud outside. Okay, I don't know how to do this. Let's try this one. Okay, please, sorry about this. Please try again.
Hello, can you hear me?
Yeah, okay. Is that better? Okay, we're gonna go with that.
Okay, great. I'll also try to be loud.
Thanks. Yeah, I know. Did you hear it through the room before? Right. So that's about what we have.
Okay, great.
All right, let's try that. Okay, one more time.
Can you hear me?
Great. Okay, we're good to go.
Okay, great. Thank you.
Thanks for for the patience. It's my great pleasure to introduce Professor Di Yang. Di is an assistant professor in computer science department at Stanford University. She also graduated from CMU. And her research focuses on natural language processing, machine learning, and computational social science. Her goal is to build a socially responsible NLP systems for positive impact. So her work has received many awards. So I will just keep it short, including the best paper nomination and best paper awards at top conference like ACL, CHI. And she is also a recipient of many like faculty awards like Intel Rising Star Awards, Samsung AI Researcher of the Year, NS of Career Awards, Sloan Fellowship, among others. So let's welcome thanks.
Thank you, thank you. Hello, everyone. Welcome to this session. And today I want to actually share something we have been thinking about in the space of design. And the title is Design to Code, How Far Away from Automating Front-End Engineering. This actually has something to do with our interest in HCI. So in fact, if you think about the design, sometimes we want to implement visual designs of websites into some functional code. This is actually a very challenging task because we need to understand the visual elements and their layouts and also translate them into structured code. These kind of very sophisticated skills dependencies also prevent many everyday users like us from building our own web applications, even we have concrete ideas of what to build or design. Specifically, I think this kind of requirement for different expertise basically make the entire design pipeline and production pipeline very complicated, since you need to have collaborations from people with different skill sets, etc., etc. This kind of functionalities, especially like from a vision language model perspective, actually could be a promising strategy to help no-code solutions. This page shows one of the related demos from GPT-4 earlier in 2023. Basically, you can actually turn a sketch into a website. So the very high level goal here is that if we could provide the model with a screenshot or a sketch of a UI, then can the model actually generate the code to reproduce it, for instance, in a language like HTML or other kind of code. So I want to share something that we have been investigating these days. It's called design to code. I'm going to take a very kind of detailed walkthrough to share a few of the key challenges we run into, especially in terms of how to define the benchmark and how to evaluate it, especially a lot of nuances around the evaluation. So this work is actually done by my amazing students, Chen Lei and Yan Zhe. Let's look at the task. This task is called design to code. Basically, what it does is that you take a screenshot of the user's website design and then give this image to the system. We hope that we can get the full code implementation. Through this implementation, we can render into the desired web page in a very kind of end-to-end fashion. So this is what we mean by design to code. Here, the instructions is text. Of course, this could be optional if you think about we just throw a screenshot to the models and try to get a code generation. Design to code, in order to kind of enable this functionality, we actually need to start with some kind of data. And unfortunately, we didn't find a lot of related work in this space. So in the very beginning, we start to just scrape all website links in the C4 validation set. So C4 is a filtered common crawl, and then we basically look at a lot of the website links, URLs, etc., etc. So the goal here is that we want to embed all this kind of CSS code. So basically define the style of those websites into a HTML file so that in the end, we only have one single code implementation file for each website or for each web page. In total, we get about 14,000 web pages, and then we did a further filtering and processing. So the overall goal here is that we want to get a set of well-formed web pages that can represent very diverse real-world use cases. I'm not going to share you a lot about the details here, but in fact, the process of automatic filtering and doing a lot of those processing actually become a very non-trivial process for us. To some extent, takes more time than the actual implementation process. And one thing we want to kind of think about here is that, of course, we can get a lot of those web pages from C4 and other resources, but how do we want to make sure the benchmark is realistic? We actually performed a round of manual curation to basically filter out those examples. So there are a few kind of considerations we have. Those web page need to have no external file dependency, and also they can be rendered in a standalone manner. So this is a big limitation at this stage. But even with this kind of simplification, we show that the models actually struggle to produce some of the websites. And also we want to make sure that the website does not contain any private, sensitive, or potentially harmful information. And then the rendered web page is well-formed. So basically we did a lot of manual processing here to make sure the data set look reasonable. One thing I want to make sure is that to mention is that we actually tend to be very aggressive in this process so that we can have really, really high quality web pages with a variety of HTML and CSS elements. So in the end, we have about 500 examples. So just to show you this kind of benchmark, it's actually quite diverse. If you think about the HTML web design, there are different types of tags you may use to induce structures in the website, such as the different sections, different head, body, or different font size, etc., etc. It's actually a very rich structure in terms of structured data. Not only in terms of this kind of unique tags, if you look at the domain that we cover in this specific benchmark, if you just like do a manual go through of like 100, 200 of them, you will see that it actually is quite diverse. The most frequent genres are websites of companies, organizations. We also have personal blogs and many kind of information sharing websites such as FAQ pages, tax policies, etc. We also have data from online forums, news articles, etc. So this actually represents a wider range of daily uses here. To kind of provide some high-level contrast here, one thing I want to mention is that the examples we have in design to code are actually much more complex on all measures, and they contain a wide variety of difficulty levels. Concurrently, there is a work from Hugging Face called WebSet. As you can see, if we just like look at the difficulty levels of certain data, we see that from a lens perspective, design to code actually have a much longer lens here. So the max output length is actually huge here. So this is going to be a unique challenge. Total number of tags, we actually have a lot of those. We also quantify the DOM tree here, which is what people call a document object model. That is, you try to represent the HTML into a logical tree there. And in terms of unique tags, etc. So overall, I think those examples in the benchmark are actually much more challenging and cover a wide spectrum of complexities than related efforts. To give you a few kind of examples here, if you look at the top are some examples from the WebSet. WebSet is a synthetic data set. And then the bottom ones are a few WebSet web pages included in design to code. So as you can see, it actually has quite interesting styles. So this is a new task. And when we first worked on this, we were very, very excited because it could help us automate the front-end design, especially given that sometimes we all want our very personalized websites or just want to have a web page to describe something like your project report. So we think about the evaluation, and this is actually not trivial here. Instead of thinking about how to evaluate, we were thinking about how not to evaluate here. If we think about previous generation of models, basically people are trying to quantify whether the generated HTML code can be compared to the source code of the reference page. And then you can use some text-based similarity metrics such as blue or other kind of edited distance. What I want to mention here is that such metrics cannot directly assess whether the visual design of the original screenshot is a reasonable generation or is correctly generated, because there may be many different levels of implementing the same web page. And also sometimes manual differences in generated code could result in major visual difference in the rendered output. So in the end, we are trying to suggest that maybe we can automatically evaluate the generated web pages by calculating the similarity between the screenshots of reference page and then the rendered screenshots of the generated web page here. So very high levelly, we are going to break down the evaluation into both high level visual similarity and the low level element matching. So in terms of the high level evaluation here, we adopted a widely used approach, which is we basically quantify the clip embeddings of the reference page and also the generated page. Then you can kind of have a very overall visual similarity of those two pages. It's worth noting that here we actually rule out the text in the screenshots because the text part is actually really hard to be rendered correctly. One thing I also want to share is that if you just look at this like clip score or similarity score, they only capture the similarity of the overall images rather than the matching of all the details like text, color, or position, etc. And then also the metric itself does not offer very nuanced breakdown. So it's really hard to kind of diagnose the weakness of models. As a result of this, we basically propose to do this element matching metrics. So specifically, we are going to look at whether the generated web pages can recall the visual elements and whether those corresponding visual elements in reference and generated web pages have some kind of alignment. To kind of deal with this, I'm going to just provide a quick formulation here. So if you have a reference screenshot IR here, and then the generated screenshot IG, we actually designed a very interesting approach to detect those visual element blocks for each web page. So basically, we want to find a block from the reference page and then a block from the generated screenshot that they match each other. So then you basically could have many such kind of matched pairs. Of course, there are also pairs or blocks that we didn't match successfully. Once we kind of get those like different block definitions or matching here, then basically we can then try to quantify this kind of element-wise similarity. From a block perspective, I guess overall we wanted those visual elements from the reference be reproduced in the generated web page, and then also those generated web page should not hallucinate any kind of new or strange elements. So we quantify this just by computing the total size of the matched blocks, which is on the top. So here, P and Q actually come from the matched block. So one block in the reference and another block in the generated web page. So we look at the total size of all matched blocks and divided it by the total size of all blocks. This also includes those unmatched ones or hallucinated ones. So the function S here will give you the size of the block. So the intuition here is that those unmatched block will lower the score as they indicate missing original blocks or generating some hallucinated blocks. And then the larger those unmatched blocks are, the lower the score is. Not only just in terms of block match, as I mentioned, there may be other factors we also look at, especially from a user perspective. There may be color match. So we basically look at the color difference to assess the perception difference between the colors of the generated text and then the reference text. We also look at positions. So basically, if you're trying to render the website, then the position of those blocks also matters. For each of those matched pairs, we basically calculate the position similarity by looking at the normalized coordinates of those two blocks. We also look at text matching here. That is, if we have two strings from two matched blocks, then you can also quantify the text similarity, which is calculated as the number of overlapping characters and divided by the total number of characters. So that's about the metrics, and happy to share more details there. This is actually a quite interesting process to operationalize a new task into a few dimensions that we can rely on. And from a model perspective, I think the very straightforward thing is that, or maybe as a modern deep learning practice, you can prompt those commercial models to deal with this task. So this is what we call the direct prompting here. You can basically give a specific instruction and with a screenshot and tell the model to actually generate the actual HTML here. And we also ask them to kind of combine the HTML and the CSS file together as a standalone construct. Because prompting is just rely on the model's understanding of the environment and the instruction. Of course, because there are some information we know, sometimes if users want to build a website, they probably already have an idea of what the content they want to put on the web page. So this is actually a very intuitive augmentation. Which means that in most cases, the user are looking for expertise in converting the design into code rather than asking the models to generate the text there. So in this like text augmented prompting pipeline, we basically just appended the input with those extracted texts. The other kind of thing you can actually deal with is that you could ask those models to do self-critique and self-revision. So basically, once we have the generated a screenshot, we could ask the model to improve the generated implementations so that the result will look closer to the reference web page. So this is what we call self-revision here. In addition to those two that we look at, we also kind of fine-tune an open source model called the Cog agent here, which is an 18 billion parameter model. And we also compare it with commercial APIs. More importantly, since website has a lot of data points, especially from a training purpose, since they are synthetic data. So we basically fine-tune this base model with Hugging Face website dataset. And as I mentioned, this dataset has a lot of like related synthetic data sets. So we only use about 20% of them to fine tune the model here. Also, one question people may be curious is that, or at least we tried a lot to make it work, is since in CVPR we have a lot of web pages, so why don't we just leverage those and then try to fine tune the model? What we found is that such training using just like random web pages from CVPR is extremely unstable. Like the training process is very unstable, and then it's also very difficult. Part of the reason could be that those real world websites or implementations tend to be extremely long and noisy. So this actually results in very low performance than training on synthetic data. So we leave this for future work to explore. We also look at a lot of like Lava and DeepSeek, and also some kind of recent models from Hugging Face. So if we look at this kind of performance, especially using the automatic evaluation metrics we proposed, very unsurprisingly, GPT-4o is the best on all dimensions. But we also saw that models like Lava 1.6, I think here the 7B, basically the open source models without a specific fine tuning here. And then with specific fine tuning, the performance of open source models can actually approach those of commercial models. So here, commercial models could be like Gemini 1.0 Pro Vision, and then you can see that DeepSeek actually has quite a similar performance compared to Gemini here. One thing we also observe is that those text augmented models or prompting successfully increase the block match scores and text similarity scores, especially those suboptimal in terms of text recognition. Self-revision actually only has manual improvement compared to other setups. I think quite a part of the reason here is that some of the earlier models could actually benefit from this self-revision, while recent models are actually quite impressive. So this kind of self-revision actually does not help a lot. If you look at the fine-tuned models that we introduce with 18 billion parameters here designed to code, so fine-tuned website and utilizing the Cog agent as the base architecture here. There are many dimensions where we cannot compare with other models in terms of the training, in terms of other dimensions. But from a relative smaller open source models, we see that the performance in terms of block match, text match, precision, and color seem to match with some of the relative bigger models. More importantly, we want to understand, like, if you give this to humans, do they agree with the overall assessment here? So following very conventional practice of evaluating this instruction following capabilities, we basically just ask humans to rank a pair of generated web pages and then decide which one is more similar to the reference. So from this page, we can see that GPT-4o is actually substantially better than other baselines. And then 4V is the second strongest model here. And then both the text augmented prompting and the self-revision prompting actually further improve the model performance over direct prompting. And also we saw that the text augmented prompting can slightly improve the Gemini direct prompting baseline. And I think intuitively those self-revision needs to basically require the model to understand the difference between the two given images, which may be a little bit harder than leveraging text augmentation. And then this actually require more modern model capabilities. We saw that website and our own fine-tuned version actually match Gemini direct prompting results. This basically suggests that fine-tuning on a large amount of data can actually match commercial models in specific domains. Since we basically use a lot of those metrics, and we also observe some interesting discrepancies between the automatic evaluation and human evaluation. So we want to see okay, if you just use the metrics we introduced to predict the win-lose rate that human provided, how should we understand the dynamics here? Basically, I think the model achieves something like 80% accuracy if you just frame this as a logistic regression. And we found that text similarity, as you can see from the table, actually has a negative impact on human judgment. In contrast, all other similarity measures actually show positive and significant association with human judgment. So this suggests that humans actually pay more attention to those like high-level visual effects like layouts, colors, and then the existence of content rather than the detailed content. This is also kind of like a cognitive bias here, where basically refers to this thing called the top-down processing. I guess what we want to share here is that human evaluation should not be blended, trusted as an oracle here, since humans may have cognitive bias to only consider these like high-level components of the website. Overall, we recommend using both the high-level similarity and the low-level elements matching, as we mentioned, to evaluate those neural models for design. More interestingly, since we sort of show that we can predict human judgment based on automatic metrics, and then we can achieve reasonable accuracy. We further sort of like provide a simulated version. That is, since we cannot get those like win rate score for every data points, what if we just like use what we have, like our metrics, try to get a predicted or simulated win rates. As we can see that overall, there is a strong correlation between our metric and those human suggested win rates. So moving forward, I think this kind of automatic metrics can be aggregated into simulated win rates to do a large-scale model comparison. I also want to share a few very interesting patterns we observed. So when the work was released, I think many people get very excited since front end always takes so much efforts. The first question we get is that, oh, actually, can the AI generated web page replace the original web page? So we basically just did several such generations and gave it to human people who we recruit from Prolific, and we just asked them like, do you think this AI generated web page can replace the original one? And around 49% of the AI generated web pages are actually considered exchangeable with the reference web page. The next question people ask is a reference web page or AI generated web page better? Very interestingly, we found that web pages generated by GPT-4V actually are preferred in around 46% of the cases. So this is actually quite interesting because it didn't align with the traditional assumptions we have, that is ground truth or ground truth or reference are always the best. In fact, we tend to see a lot of the creativity or neural patterns here that those AI generated web pages seem to work better. Why? I think the other hypothesis when we were trying to do our analysis is that the current model like GPT-4V seem to have more access to modern and popular web page design or design principles so that they can automatically improve the original design. So the data set that we have, especially from C4, a lot of them tend to be like relative old designs. So this actually opens up many new opportunities for future work to think about website design improvement, etc. To give you just like a few kind of examples. So the left side is a reference web page, and then the right side is the model generated. And then if you look at the generation, overall, I think you get the components correct, although the specific layout may still not be there. So this is all what I want to share about design to code. And since we work a lot with like front-end designers, another question we run into is people were curious like, since right now you still have a screenshot, what if I can just use Sketch? So if you look at my screen, this is a very interesting sketch. And this sketch may be converted into this website. Or if we look at this like very high level abstract sketch, and this could be generated into a specific website. So there seems to be a huge amount of needs to look at a sketch. So a follow-up we are thinking about is actually constructing this sketch to code from design to code, where we borrow this like wireframing conventions, where you can actually like use different patterns to mark specific regions and then use this to do the generation. The corresponding evaluation needs to be refined, and I'm not going to go into the details here, but you can leverage a lot of the evaluation we have for design to code and also consider the layout similarity here. More excitingly, I think since this is going to be such a big project, we can actually get agent to do this. They can ask questions. They can also receive feedback in this kind of specific fashion. And when we get this kind of different functionalities or give agents agency to deal with this, we saw that overall they tend to perform better when they have the flexibility to ask questions and to also receive feedback from users. I think there are a lot of exciting direction here in terms of how to go beyond the screenshot, the sketch, and how to leverage dynamic web pages to test the model's capability, as well as better evaluation. Overall, I think there are lots of details I want to mention in terms of how to get a good benchmark. I think this has been a topic people chat a lot, and in terms of how to set up the right benchmark here. And also in terms of where and how human feedback can actually intervene. I think especially in the increasing interaction between humans and vision large language models, the role of human feedback is actually getting more and more exciting to think about, where human feedback could actually intervene for us to have better interactions and performance. And more importantly, I think we have been kind of going into this, what we call evaluation crisis, where it has been more and more challenging to evaluate models. I think there is no like single answer here, but a few dimensions I want to share is just thinking about how are we evaluating, what is being evaluated, who is evaluating, and when do we evaluate. And this actually could help a lot in terms of the ecosystem. That's all I want to share. Thank you. Happy to take questions.
Thank you very much, Dee. Any questions in the room for Dee? Please.
I have one question, and for your model that you input is screenshot or sketch, and but for the industry, the people usually use the Figma for the UI interaction. I wonder if your model is for the make it the Figma input.
So the question is, the model currently takes in an image, but many industry use like vector tools like Figma, for instance. Do you think you might be able to take input from a system like Figma?
Yes, so we have actually, this is a great question. We have been actually talking to Figma and also exploring other kind of modalities. As I showed in the talk, even just like a slightly moving from design, this kind of screenshot to sketch, we see that the performance actually drops a lot. So eventually we want to make this kind of facilitation tool for designers so that if they just like play around with Figma design or interface UI, and this can actually get to like a rendered web page so they can see it dynamically.
And we have a question in chat from Yu Sun. Modern front-end pages are complicated with JavaScript,
Yes.
including animations. So
yeah.
How might we build a benchmark to consider this too?
Yes, this is also a great question. So in consideration, so the issue with JavaScript is that you need like users to go there and click each of the buttons to see all the rendered results. And so it will have like a lot of dependencies between different pages and like external actions, etc. So I think this is actually a great next step to think about how to actually leverage these very interactive agents to interact with the website and then also kind of generate the code along the side.
Thanks, Dee. Let's thank our speaker one more time.
Thank you.
All right, at this point, we break for the poster session. So those of you with posters and everybody attending, we have to leave this building, go over to Arch, which is out the main door, over the street, 1 block, and then down a little bit. So out the main door, over 1 block, and then to your right. Once you get into Arch, you'll see big elevators, 3 of them, taking you up to the 4th floor. This is the main exhibit hall where all of the poster sessions are, and the main exhibition for the industry will be in a few days. So your numbers are on the webpage for the poster sessions. Please find the AI for CC section. We will see you there very shortly. We resume back in this room after lunch at 1:30 p.m., where we have Aaron Hertzman from Adobe, who's going to talk first, leading off the afternoon's events. So let's go to the poster session and see you all soon. I know.
Okay, welcome back, everyone. Let's start the afternoon session. So first, we will start from the oral session of the workshop papers. And first, let me briefly introduce the paper reviewing process. So we have about 52 submissions, and among them, 36 have been peer-reviewed, and 22 have been accepted as posters, and 4 papers have been accepted as oral presentations. There are also 14 directly accepted papers because they have been accepted by some other venues like ICCV or CVPR this year. And there are in total like 40 papers presenting at the workshop. And here is the award selection process for the best papers. So only papers that have not been published elsewhere will be considered for the award for best paper. And a committee of 3 PCs will review the top scoring papers to decide the best papers. And we also have a best poster award, which the committee or award committee will watch all the poster presentations and then decide after the workshop. So if you are presenting a poster, yeah, please do it well. Yeah. So next, I'm pleased to announce the best paper runner-up. Is by Amber Yijia Zheng and Raymond Ye for their paper toward safer AI content creation by immunizing text-to-image models. And the authors come to get your certificate if you are here. Congratulations. So next is our best paper award, which goes to Jessica Young, Junho Kim, Yunjae Choi, Guiyang Li, and Yongzhang Oh. Yeah, sorry for my bad pronunciations. Congratulations. So next, let's come to our oral session. The first one is the best paper award winner, visual style prompting with swapping self-attention. Justin? Let's hold the question towards the end. So there will be a Q&A after all the presentations.
Hello. My name is Jessup, and I'm from Yonsei University. And I'm going to give you a presentation of my work, Visual Style Prompting with Swapping Self-Attention. I'm interested in making a lot of cool images with stereo diffusions. Okay, let's begin. So let's assume a scenario. A user wants to create new content in a specific style. In this case, let's assume this locally styled horse. One of the naive approach is to describe the style using a text prompt. However, even the detailed description fails to synthesize the target style. Now we know that text is not enough to control the style. To address the problem, we introduce visual style prompting, which enables the user to directly specify a style with a reference image. Through ours, users can generate novel content specified by a text while precisely reflecting the style of the reference image. We would like to showcase our results first. So as shown on the figure, only ours precisely reflects the style, such as color, texture, and pattern, and even material of the reference image, and makes novel content made of cloud. And similarly, ours successfully generates novel content in the style of burning wood in the reference image. In addition, ours is good at preserving the content of the original denoising process. Compared to ours, competitors change the content of original denoising process while reflecting the style of a reference image. This good property reduces the content leakage and enables ours to synthesize more diverse layout and composition compared to the other model. It also helpful to get enhanced control using text. So for example, the other often fails to synthesizing the object in here, zebra. And compared to the others, specifically style align, ours can synthesize poses such as learning, and can synthesize a single object specified by the text prompt. Lastly, ours is well compatible with existing methods such as ControlNet or Dreambus LoRa, which is a necessary part of current creators. Key idea of visual style prompting is so simple. It is swapping self-attention between original denoising process and reference denoising process. Simply applying swapping of self-attention to all layers results content leakage, as shown on the figure. To address the content leakage, we adopt swapping self-attention only at the output. In addition, we provide a simple but effective strategy to use real image as a reference. Our method consists of two denoising processes, a reference and original. To prepare reference denoising process with real image, we suggest to use a stochastic encoding. It reduces artifacts and helps better reflection of target image. It also works well with self-attention variants like Masa control and style aligned, which is accepted here in CVPR 2024. This is the end of my presentation, and I put the interpolation result between the reference and the resulting images, which demonstrate how well the style is reflected. If you have any questions or would like to discuss further, please come by our poster. Thank you for listening.
All right. Hi, everyone. I'm here to present Loop Draw, a loop-based autoregressive model for shape synthesis and editing. In this work, we want to explore alternative ways to represent shapes for editing. Explicit representations, such as meshes, accurately describe the surface, but editing on their elements tends to have overly local effects. In this work, we propose a loop-based representation, which when coupled with a neural model of shapes, loops are explicit descriptions of cross-sections of shapes, but coupled with a neural model of shapes can serve as a representation that enables intuitive shape editing that can apply larger scale geometric effects. We were mainly inspired by Sketch RNN, whose stroke sequences enable interesting sketch editing features. How might we do this with loops in 3D? In Loop Draw, we make our tokens planar closed loops. Given a known set of planes, the token vector consists of coordinates describing the closed loop, as well as a plane up flag to indicate finishing the current plane and to begin placing the next loops on the next plane. Here's a closer look at the way meshes are sliced to obtain this loop sequence data. A slice plane that cuts the mesh at 3 loops, for instance, as shown here, will yield 3 tokens in the sequence ordered in descending order of area. The vector of each loop has a fixed number of points resampled from the original intersection. Alongside this, there's a plane up flag that is 1 for the first loop token in a plane and 0 for the rest. Having this loop sequence data obtained by slicing the meshes, we then put it through a standard sequence VAE model, where the encoder and decoder are both stacks of self-attention transformer layers. The encoder summarizes the loop sequence into an embedding that is then mapped to a latent distribution, which is encouraged via KL divergence to be standard normal. The decoder then samples latent vector and predicts a loop sequence that is penalized via L2 reconstruction against the original input loop sequence. To obtain shapes for testing and viewing, we estimate planar normals on the loop points and use Poisson reconstruction. Given this method, here are some of our results, editing results on cosec vases and ShapeNet sofas. Given some shape predicted from a latent code, such as this vase, if we were to intercept the autoregressive decoding at the red loops and rerun the decoding for the subsequent loops, for instance, by scaling and shifting the target loop, we get novel geometry completions. In this case, the upper portions of the vase adapt to explain the new handle suggested by dragging out the one scaled down loop. This shows a natural editing method that allows for larger scale effects from tweaking one or a few loops. We can also switch out loops for handmade shapes like squares, resulting in adaptations like these. We can tune the parameters of this insertion, such as their position, number of loops, shapes, and sizes, to obtain tunable, diverse shape variations that are not just simple rescales while preserving features of the latent code shape. We can also bring over loops from other shapes, transplanting them into the decoded shape. Here we bring over a 2-handle portion from another vase, triggering the completion of a novel set of handles for the targeted face. Here's another transplantation, this time on some sofas. In both cases, the continuation of the sofa decoding smoothly transitions from the transplanted segment back to the targeted sofa style. We'll let that play one more time. We also see that our edits can compose together. In this example, we can first insert some custom square loops into the first blue segment, resulting in the first reinterpretation. We can then go back and add a transplant, the base of handles from another vase, which grows handles on top of that reinterpretation, showing that our edits are also composable, allowing for an extra way to explore the space of possible shape modifications. Lastly, being a VAE-based method, we can do unconditional sampling of shapes from latent space with reasonable geometric variety, as well as latent space interpolation of shapes, showing the smoothness of the learned latent space. In summary, we do sequence modeling for hierarchies of cross-section loops that enable shape editing, completion, and generation that is controllable, allows non-local effects, and is composable. Further directions to take this work include using loop-specific reconstruction methods, as well as more sophisticated representations that allow for arbitrary slicing axes, planes, and more elaborate geometry. That's it. You can check out our implementation at this link, and thank you for listening.
Hi, I'm Amber from Purdue University, presenting tools safe for AI content creation by immunizing text-to-image models. This is a joint work with my collaborator, Raymond. With the advancement of open source models, content creation has been easier than ever before. We can just use several prompts to generate some amazing pictures, like pictures in the style of Disney, or even something out of our imagination. However, there's also an increasing risk that these models can be used to learn some harmful concepts. For example, generate artist's work without a permission or something inappropriate. In this talk, we use malicious adaptation to subsume this kind of misuse of models. So what can we do about it? One approach is through concept erasing. Given a pre-trained diffusion model, which can generate specific concepts, an erasing algorithm can modify the model weights to forget these concepts. As a result, the model is no longer be able to generate these concepts. However, remember that this model is open source, so the user can use some fine-tuning method, such as Dreamboost or LoRa, to relearn the erased concept back. To prevent relearning, we need some forms of protection against a malicious adaptation. Prior work studied how to protect by using data poisoning. For example, given some photos of a colorful guitar and a pre-trained diffusion model, the model can learn to generate that guitar with adaptation method A. By modifying images with imperceptible changes, one can poison the data such that the guitar cannot be learned. So in this case, the responsibility to avoid the malicious adaptation is placed on the content creators, which means the content creator needs to run some protection algorithm before they release their content. But is that the only way? In our work, we consider protecting the open source model prior to releasing it. That is, we propose to immunize the model against a malicious adaptation, in short, IMA. Following a bi-level optimization framework, IMA aims to modify the pre-trained weights such that it is difficult for the subsequent adaptation algorithm to be effective. In a lower task, IMA runs the exact algorithm from A. And in the upper level, we flip the sign and maximize the loss and only modify a subset of the model weights. This creates a bad initialization for the subsequent adaptation. As a result, the model with immunization fails to learn this harmful concept. So with IMA, we shift the responsibility for preventing malicious adaptations from the content creator to the model releasers. Here we show the effect of IMA on the task against relearning on an erased model. As can be seen from the graph, Using LoRa, the model gradually relearns the erased Picasso style, as evidenced by the increasing similarity to the reference images. This shows that the model doesn't truly forget this concept, and people can still easily reverse the process to relearn this concept back. Now with IMA, the use of LoRa becomes less effective. The generated images show significant deviation from the reference images, indicating that the erased concept was not relearned. Here are more qualitative results. We show both styles and objects. The erasing algorithm can erase the target concepts. However, without IMA, these concepts are relearned after adaptation. In contrast with IMA, the concepts are not relearned. More results are presented in the paper. So in conclusion, our work highlights that the unlearned concepts can be relearned through fine-tuning methods. And we believe that the responsibility for preventing malicious adaptation should lie with the pre-trained model releaser, not the content creator. Therefore, we propose a new paradigm to protect models against the malicious adaptation instead of the data. To learn more about our work, please refer to our project page and our poster. Thank you.
Hi, everyone. It's nice to see some familiar faces here. My name is Albert.
I'm Maxim.
And today we're presenting array straw. One red block on top of one blue block and one yellow sphere on the right. A few months ago, when we started this project, this is what Stable Diffusion gave us. Since then, models have come a long way. As you can see, more recent models can nail this prompt, likely because of much better language embeddings. But once we dial up the complexity a little bit more, things start breaking down again. And this happens for more natural prompts as well. In this example, we want to generate a cat on the kitchen counter, but instead we get it on the dining table. So here's our intuition for what's happening. The prompt complexity on the x-axis here represents the amount of details in a prompt. So far, it seems that just to add a few more details to the image, we have to scale up these models an order of magnitude more. Analogies to humans are often imperfect, but the artists that I know don't work in this way. Once they learn how to draw a cat, they can draw it in any context. They can basically compose arbitrary concepts in any way they want. And this hints at a compositionality of the image generation task. Existing models attempt to learn the joint distribution of every object that can appear in a prompt. But humans can factorize this distribution and generate the image step by step. If they make a mistake, they can go back, fix this mistake, and successfully finish the task. Now, can we build a computational model of this? In other words, can we leverage this compositionality? One thing we can try is start with a blank background, and we can insert one object at a time. This goes into the domain of image editing. And fortunately, people have been studying this. Unfortunately, prior models don't do a great job at inserting objects. They're better at stylistic edits. So, like any sane person would, we train our own model. And the way we did this is kind of neat. The most straightforward way to learn object insertion is through input-output pairs. But how do we get this data? Our key insight is that we can collect this data using object removal, aka inpainting. In more detail, we start with some unlabeled arbitrary image. We caption it using a vision language model. We detect the objects in the captions. We segment them, we erase them, and in the end, we get some data that looks like this. We repeat this process for about 50,000 images. At training time, we give the model the edited image, we tell the model what we just erased from it, and we supervise it towards the original image. It's also important here to note that we're not training this model from scratch. We initialize from Stable Diffusion and allow for image conditioning using some zero initialized channels. Starting from this pre-trained model is very important for generalizing beyond our training data. Despite our simple framework and a relatively small dataset size, we get some surprising results out of this. Our model can insert nested objects. It can generate non-rigid objects such as this water flowing. It can even generate objects that involve occlusions. It can understand human affordances. For example, it knows how to put this water gun in the person's hand. It can edit art and even generate transparent or reflective objects. Pushing this even further, we found that our model can learn the natural distribution of objects. In this utensil drawer example, we give our model this empty drawer, and our model can tell exactly where and how to insert these utensils. This has a lot of applications for embodied agents. All right, I'm passing to Maxim here.
Yeah. Finally, back to our original premise of generating very complex and detailed images. Imagine you're a content creator who creates an advertisement or a movie where you want this scene in a park. You see a park, a wooden bench, some people on a bench, a yellow bike, and a tree. Maybe it's a romantic comedy or something. And if you pass this image directly to our base model, you will not get a complete image with all the objects you wanted. In this example, for example, you don't get the bicycle. Our model can handle this. The way we handle this is with iterative generation. We pass a complex prompt which includes many details to a large language model. We break it down into simple atomic edits, and we apply our model to generate each of those edits. In the bottom example, you can see another example of this, where you want an office room with a giraffe, and the base model fails to insert the giraffe. It forgets about it, and our model does insert successfully. Here's another example of how it's very fun to play with. You can start with the same room, and you can get to a kind of business classy hotel lounge, and you can also get to this homey Christmas room. Yeah. Finally, we came up with a way to automate this whole process. The way we can automate this process is through beam search. Because we operate exclusively in the text domain, we can evaluate the quality of generated edits using clip score. So for example, if you want to generate something with 10 successful edits, we would break down the prompt into 10 edits. We would pass each edit to our model. We would rank the outputs using clip score, and then we would choose the best one to continue with the completion. This is an example of how it can significantly improve image generation quality. Yeah, this is an example of what beam search looks like. So we want to create this like breakfast plate with pancakes, butter, syrup, and a coffee cup. And we break it down into simple edits, and we generate many versions of each edit, and then we select the best one at each step. And this way we can leverage our computational resources. Very important emphasis here is that this scales very well with number of edits. If you have an object with 20 objects, 30 objects, this will work well, and Stable Diffusion will not handle that. Back to you, Alper.
Thank you. So why should you care about array straw? There are two branches here. On the data end, array straw is a way to generate data. So it's agnostic to your model architecture. It can be used for any image-to-image training recipe. And the quality of the data is upper bounded by the annotation models. Vision foundation models have been getting really good recently, so we should be able to scale up this data and get very high quality array straw type of data. On the model end, we find that our model can perform high quality single step insertions, which has applications in editing, interior design, robotics, etc. And finally, our last point is that a model trained on array straw data can generate more complex images than its base model by composing images step by step, kind of like a visual chain of thought. For more details, we highly recommend that you check out our website, and we also have a poster session coming up, so you're all invited to that one. Thank you.
Thanks so much.
We're a little bit over, so let's move on to the next speaker. And we just need to switch the laptops.
One of the papers in computer graphics
Okay, so people on Zoom should be seeing audio and video now. Okay, hopefully people on Zoom are seeing the slides and seeing me and hearing the audio. Great. Yeah, thanks so much for having me here. It's a real pleasure to be here, of course. Just a little bit about my background. I studied art and computing in college and then PhD in computer science. So I like to spend a lot of time painting and drawing as a hobby now. And a lot of my work has been on computer graphics algorithms for making pictures that mimic or enhance existing artistic styles. And this includes work that I showed as part of my PhD in New York in 2001. There's a painting that you walk up to it, and the painting continually updates as you move in front of it. So I think in the past 15 years, the past 10 years or so, there's been this real sudden excitement now coming back to computer-generated art. And I trace this to the deep dream method. This is where like the first glimmers of something was happening with deep dream and inceptionism that was exciting for a week or so. And with the first art gallery version of this was shown in San Francisco, hosted, sponsored by Google, and this is based on deep dream and neural style transfer. And then it started to get parodied a bit in the media. I'm going to try the audio here may or may not work, but we'll see how it works.
Painted it. I like it. It's really cool. So who painted it? A machine.
It's actually the first work of art made by AI to be sold at Sotheby's.
Were you able to hear that? You're okay, great. So this was a satirical TV show making fun of Silicon Valley, talking about AI art being auctioned by Sotheby's. 6 months later, AI art was auctioned by Christie's for €500,000, and this work was signed with the loss function for GANs. So lots of strong claims being made about the role of the computer here. Then, of course, text to image was first experimented with VQGAN and VAE, and clip loss, and then DALL-E came out, and now everyone's talking about this stuff. Within the computer vision, computer graphics world, there's people making interesting claims. So I really like this CAN paper from Elgamal et al. It's really interesting ideas. But they say in their abstract, we propose a new system for generating art. The system generates art by looking at art and learning about style and becomes creative. This is a really strong paper, claims being made in the abstract of this computer vision, computer graphics paper. This paper was picked up by the media, and headlines say, artificially intelligent painters invent new styles of art. Or going down the food chain, Daily Mail, the AI artist that can create its own painting style, and critics prefer its work to human efforts. So there's a real strong distinction being made between the human and the AI artist, like these are two separate things. And so let's see how this spreads. Here's Jerry Saltz, who is one of the preeminent art critics in the world. And the thing to see here is the agency he assigns to the algorithm, to the AI artist.
Initial thoughts, incredibly dull, generic, boring. The program.
We have this funky audio setup. Let me try again.
Initial thoughts, incredibly dull, generic, boring. The programmers are not freeing up the program. I want the robot to tap into its inner robot. Be free.
So from the abstract of a paper in archive to art critics saying this stuff is just not very good artists. So throughout this whole history, there's this long discussion, people debating, can computers create art? And often I hear people talk about it as if it's just a matter of technological capability. If the AI makes good pictures, that makes the AI an artist. On the other hand, often talk to people at least informally, or people outside of computer science, and they say, of course not. Art requires intent or requires expression. And I think that there's an intuition a lot of us have, some people have, that it's a human activity, or it's like having a soul or expressing your individual humanity. And I share this intuition, but I feel like we could make it a little more scientific or a little more a more solid footing. And I want to make a couple of points here. First is that I believe software offers technologies for people to make art. It is not the artist itself. And there are many other technologies that have been like it before, which I'll mention. And so as a result, I don't think we should consider computers or AI as themselves the artists. I do think they're going to have a lot of impact on how we think about art and how we make art. And that historical technologies, many other examples from the past that have had similar relationships with art, provide us with useful lessons for how to think about what's happening now and what will happen in the future. So in this spirit, I want to review a few examples of technology that has transformed art, and I'll focus on one in particular. But one quick example is oil paint. In the 15th century, people would paint with fresco, and if you read about fresco, it has a lot of practical difficulties. You have to paint it in sight, you have to work fast. It has a limited range of tones, whereas oil paint was much more convenient, and you can get much richer visual complexity and richer dynamic range with using oil paint. And one artist have said, quotes Michelangelo as saying, "Oh, this new technology, this is for amateurs. Oil paint is too easy." In the Western tradition in the following centuries, one sort of development in art was the ability of artists to make more and more visually realistic works. They're sort of dazzling in their visual complexity and visual realism. And I think for us, it's maybe hard to appreciate just how significant this was. We are surrounded by photos and pictures and magazines and movies and on our screens all the time. 200 years ago, you could not see pictures like this except by seeing the work of a highly skilled and talented artist. And so the identity of what an artist was, or at least what a painter was very highly tied into the ability to make good pictures in some sense. So the rumblings came from photography. This is the first known historical photograph by a guy like basically effectively playing around his garage with some chemicals and light, and a bunch of art amateurs and experimenters tinkered with it and played with it and saw what they could do. They Instagrammed their food and they took selfies. But the real kind of impact became, or the real threat became apparent with Daguerre's public presentation of the daguerreotype. And he made the technology, he described how to use it, and the French government bought him out so that he wouldn't patent it because they viewed it as being of benefit for the public. And within the initial demonstrations of the daguerreotype, famous important artists like Turner said, "This is the end of art. I am glad I've had my day." And you can imagine if the identity of the artist is making pictures, and now here's a machine that makes pictures, it seems like it kills art, it makes artists obsolete. So what actually happened? Well, the reality is far more complicated. One use of painting was for portraiture. So if you want to, like today, we want to have pictures of our family and our friends and ancestors. And at the time, the only way you could have such a picture was by being very wealthy and hiring a painter to paint your portrait over a long period. In the middle classes, you could also have silhouettes made, which are cheaper and simpler, but obviously not great likenesses. And so once photography became more widely available, it replaced a lot of portrait painting studios, and portrait painters often either lost their work or had to retrain in how to do portrait photography. And within a few decades, one painter looks back and says, photography has harmed painting considerably and has killed portraiture once the livelihood of the artist. So this was painters used to do portraits to make a living, and then they weren't able to. In the more high-end art world, there's a long discussion over whether is photography art. And on one hand, again, there's the tinkerers who are playing around photography and seeing what happens when you make images with it. And they develop their skills and experiment with what happens with the art form. And by the beginning of the 20th century, photography was really seen as a separate art form, accepted by the major cultural institutions. And people were making pictures with photography that were very different than people had been making with paint in previous centuries. On the other hand, there were the haters, like grumpy Charles Baudelaire here, who wrote in the review of a salon, if photography is allowed to stand in for art, it will corrupt it completely, thanks to the stupidity of the multitude. So I see people taking pictures right now, and so this is us. Now, but artists actually recognize this as a challenge. So Whistler wrote, I'm sorry. All right, must be a barge coming through.
One.
Okay. All right, so Whistler wrote, "The imitator is a poor kind of creature. If you paint only what you see before you, then the king of artists would be the photographer. It is for artists to do something different." And so his response was to make these sort of atmospheric things, because that's something that people weren't doing with photography at the time. Van Gogh wrote in his pivotal year of 1888, wrote to his brother, "Accurate drawing is not the essential thing to aim at, because reflection of reality in a mirror would not be a picture at all, no more than a photograph." So now artists are thinking, actually, maybe making realistic pictures isn't what art is about anymore. And maybe photography isn't even art because it just does the thing we were used to be doing. So in summary, it looked like here's a technology that automates art. Many artists feared it, disparaged it. What actually happened was we have this new art form, photography, which is very different from the old ones. The old art forms were invigorated. That I would say that the whole modern art movement, maybe it wouldn't have come about if it weren't for photography, because it really challenged traditional notions of what art was. Jobs were affected, so people who were doing portrait painting and certain kinds of postcard painting weren't able to keep doing that anymore. But one of the things which I didn't mention is that making certain kinds of images is now available to people to hobbyists. We're all carrying cameras and taking pictures all the time in ways that we wouldn't have been doing if we had to be, carrying around brushes and paints. So there's a lot of different things here. It's very complicated. It's not just one single, the technology kills art or it saves it. These different trends, I would argue, repeat a lot with many different art technologies. So there's other examples of art technologies that have an important impact, and many of these things recur with them as well. So with this modern art movement, it became there's kind of a sense that now, like, almost anything can be art. Almost anything an artist does can be art. There's more complicated philosophical descriptions of this idea in the theoretical sense, but let's just go with this simple statement for now. One of the more interesting developments within the contemporary art world is the notion of conceptual art. The idea that it's really the idea that makes the art and not the execution. And Sol LeWitt, I think, is he's both an important writer and artist in the development of conceptual art, but also I think has implications for computer art as well. He wrote that the idea is the machine that makes the art. And these works here, these wall paintings, are ones where he wrote a set of instructions for where all the lines go and what colors to use. And then someone else actually does the painting, but Sol LeWitt is still the artist in his work. And if you saw Jason Salavon's talk this morning, he also referenced Sol LeWitt. So in the 1960s, as soon as people could start making pictures with computers, they started experimenting with making art. And it's long before 3D computer graphics or anything, when you're just like doing a very, very primitive coding. People were starting to write pieces of code that made pictures. The one on the very left directly references a Mondrian painting, and they actually there's a paper in a psychology journal where they ask people which one looks more like a human-made art and which one do you like better, comparing the computer-generated one to the Mondrian. And it's an interesting reference point for modern user studies and crowdsourcing in evaluation of AI art. And their work did pretty well compared to the human-made Mondrian. One of the most important AI artists of the 20th century is Harold Cohen. He came from a very contemporary art-focused background in Slade School of Art in London, and he started out setting rules for himself, very conceptual, I should say, and setting rules for himself about how to draw. And he would draw these things on paper that followed those rules. Then, when he discovered computers, he said, "Well, why am I following the rules myself? I'll just write some code." And he spent the rest of his career writing more and more sophisticated programs that generated art themselves, and even made printing software that print out with robots the things which are generated by his code. There was a recent review in the Whitney Museum, if you were in New York recently, of its work that was very nice. In the more commercial or more popular arts, computer animation is something that people have often perceived as being, oh, the computer just does all the art. But it's really something which came about from a close collaboration of artists and scientists. And there was always the initial fears. So Ed Catmull and Alvy Ray Smith, who ended up founding Pixar, before they did, they would go down to Disney and try to convince people at Disney to use computers. And they found that the animators were always frightened of the computer. They thought it was going to take their jobs away. And they spent a lot of time telling people it's just a tool, it doesn't do the creativity. And if you ever tried to use conventional computer animation software, you know, it's really, really, really hard. And a lot of the skills of making a computer animated character come to life are the same skills in hand-drawn animation. And now, when we look at any modern feature film, TV show, there's just pages and pages of credits of people who are employed in different aspects of computer graphics. And this includes things that you wouldn't think of as being visual effects movies, that, or they claim there's no CGI, and in fact, it's all, you know, all the jets and Top Gun are actually computer graphics when they say there's no CGI in the movie. In my own work, I started out just writing code that would take a photograph and make a painting out of it, and I would just directly implement rules based on my own experience in painting. And you can read my SIGGRAPH 98 paper and see all the decisions that were made in this algorithm that makes paintings for you as you move in front of it, that I mentioned earlier. And I got, you know, but I found it difficult to figure out how to make all those, you know, specify all of algorithmic decisions. So I started thinking about learning from examples. So this is from a paper from 2001, where I transferred patches from the example on top to generate the output on the lower right. So this is basically the first example of learning-based style transfer. But the you can still read the paper and understand all the decisions that are being made and how they're being made, even though there's a lot of automation involved. And I think that's true for more recent style transfer methods, even though there's more and more abstraction away from the code part. Throughout all this, you know, history, there are the headlines. This robot can paint, but is it art? Which is describing a nice painting robot from CMU. This is New York Times in 2023. 40 years earlier, in the Amiga world, computer art, is it really art? And so people are asking this, you know, decade after decade. Even in the 1960s, people were asking this. So we have this 60-year history of people making art with computers. Every decade, people are saying, is it really art? Is computer art really art? Maybe the computer is the artist. And every decade in the past 60 years, people say, no, the person running the computer, using the computer is the artist here. The computer is a tool. And all this art is human-made. People wrote the software, people run the software, they operate it. If there's training data, they've supplied the training data and so on. And then maybe there's authorship is diffused through a whole bunch of different people, but it's all human-made art. Now, this parallels, of course, all the AI hype that I think we're all aware of now. And this also had this long history. Here's the first announcement of the perceptron in 1958 by Larry Rosenblatt, where the New York Times headline says that the Navy announced that this new computer will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. And this is from a linear classifier. So, you know, summing a bunch of numbers and multiplying them, well, you know what I mean. So all these things we're calling AI, it's really technology. It's not magic. And we need to understand it in the context of it is a new technology with new properties, like many other new technologies that have come about in the past. And as you know, most of what these modern things are doing are fitting, you know, like the LLMs and diffusion models. They're essentially fitting very high-dimensional, very complicated nonlinear functions to large data sets of data points. And then there's some wrapper code around it that tells it, oh, say, as an AI agent, I can't do that or whatever. And we have, I think, a very strong propensity to view artificial systems or non-human systems as being alive. You know, our ancient ancestors would see the sun and the stars and the trees and see them as being having souls. If you're not familiar with the ELIZA chatbot experiment, it's very relevant. And basically, Joseph Weizenbaum, who is a critic of AI, wrote this very simple AI chatbot that's like a Rogerian talk therapist. And it says, what are you thinking about? What is troubling? And you chat with it, and it basically keeps asking you a question like a talk therapist. And he left it out in the computer lab, and students were having these really intense discussions with it. Like people get really involved, and they don't they kind of treat it like it's a person until you see the code. It's basically like 20 conditionals or something. Another, I think, example that illustrates how we can get seeming creativity from simple systems are the Mandelbrot set, which was big in the 80s. If you watch videos of it, it's just dazzling. It's so cool, and it's really fun for a while. And it's unpredictable, and it's 10 lines of code. It's chaos theories you cannot predict. Chaos theory tells us you can't predict how it's going to behave. It can make surprising, new, interesting, visually dazzling stuff for a long period of time. And yet, it's hard for me to imagine saying these tens of lines of code are an artist. Now, when I have discussions about this with people, especially in computer science, I think also outside too, it feels like there's some people have this very strong feeling that being an artist is just about making good pictures. That if the machine is if you have a piece of code that makes good pictures for some notion of good, then that makes it an artist. And as you might imagine, I don't agree with that.
Can a robot write a symphony? Can a robot turn a canvas into a beautiful masterpiece? Can you?
So I would point out, as I have, that we have a history of over 150 years of machines that make art, from photography to early computer animation to these new machine learning things have been called AI in various ways. And none of them have been widely accepted as themselves the artists. You know, people make provocations and they say it's the artist, but these tools have never been themselves accepted as artists, even though with a camera, you press a button and it makes a picture, it does what artists do. And so I really think we should think of computers as being yet another technology that are tools that people can use to make art. And the way is going to be very different with new technologies, but they're still technologies. So we can still ask, though, will computers ever be considered artists? Will this change? Will there be a wide societal acceptance as some piece of code as an artist? And when I talk about computers, I'm really talking about these things. I'm not talking about some hypothetical
GCP. Yeah, without further ado, the stage is yours.
Yeah. Okay, so thanks, Adrian, for the nice introduction. It's also my great honor here. I think today I will just talk about a lot of our recent works on this multi-model-driven AI. So mostly I'm working on the 3D domains, but I will also talk about some of the 2D works, right? So I'm Zui, I'm from NTU, Singapore. I think this here is a kind of a prediction, like back in 2 or 3 years, by some very famous consulting company. That is by 2027, the creators don't have to be technical, just have to be created, thanks to all the automation tools. And I think after all this progress in the recent 1 or 2 years, we can safely change into 2023 or 2024, right? We already have very powerful tools. Now I just have to figure out what is the right way to create art, and also, as Aaron has just introduced, and also how to combining and also how to control the tools. And this AI generated content has a lot of applications in movies, in games, anime, VTubers, like virtual being. If you just see the whole pipeline of the creative industry, from the script to the layout to the 3D to the final visual effects to the shading, rendering, you can see many of them already being replaced or facilitated by AI technology, right? So on the 3D domains, we have a lot of journey models. On the script side, we have the large language model, and also in the film side, in the visual effects, we also have a lot of like graphics tools, right, nowadays. So I think some of the works are just fit into this 3D and also video side. So today I'm just going to introduce my work from 3 perspectives. Of course, avatars, objects, and things. So avatars, I think, is the most commonly used ones in a lot of applications. It's also, I think, the subfield that's been achieving the most progress, because human body has pretty rigid like part. We can define in the kind of inner structures and also try to do the rendering quite well. Then we can go to the object. I think objects 3D or 2D have achieving very rapid progress thanks to the large scale data set, right? So for the 2D images, we have like Leon, and for the 3D, now we got like Optiverse. Of course, we have also working on something that also to complement the data kind of creation. And finally, I think is the hardest part. That is how to create large scale things, right? So on the first side is large scale. It's not just like the avatars or objects that's a limited space support. On the other hand, it's also has lots of more diversity and complexity out there, because we want to deal with both like indoor scene, outdoor scene, city scale, like also rural scale, something like that. So we are also trying to make some initial attempts on that side. Of course, first I will talk about the avatars. So the first work I'll talk about is called like the hyperhuman. So it's kind of appearing in iClear 2024. It's a collaboration with Snap. So compared to the original, like the stable diffusion you have been using, so I think one of our main contribution is to introduce the human prior into diffusion models. Right? You can see without just the RGB diffusions, we also have the depths, also have the skeletons, and also have all this surface normal there. So we show that if you just want to work inside the specific domain, you can use domain knowledge, such as like the human pose and also the depths, the surface normal, into the modeling of the diffusion models, right? We can train them together. Of course, to prepare high quality data, you need to tweak about the cleaning, the annotations, how to get those annotations efficiently. That's a problem. And here is some of the results. You can see we can do it on condition generation as well as condition generations. You can specify the pose, specify also the surface normals. You get pretty nice results. So I've compiled our method with like stable diffusion, FXL, as well as like control nets. You can see the human faces, the human kind of holy structure is better. And here is kind of demo videos. So the bottom row is the prompts we given, and the image is generated. So you can generate like 1K images according to this prompt, like man sitting in the bus, looking away, or we can generate even these interactions of two persons with a teddy bear, and very complex, these interactions of human hands and the plates, and zoom in, zoom out. Okay, so the time limit for this work I've just shared here. If you have interest, you can check out our project page. So after that, we started working on this like 3D human domains. So one challenge of applying the diffusion models on the 3D human is that how to choose the suitable representation. So for the 2D humans, you have rigid discrete. But for 3D humans, how to choose, right? So how to balance between the efficiency and also this modeling capability. Here we advocate using these volumetric primitives, right? We find that it's a very good way so that you can leverage the power of diffusion model as well as doing this very good real-time renderings. You can see we generate 3D humans by denoising on these primitives instead of like on the mesh or on the kind of textures. So after we get in the results, we can do other things like novel view, novel pose, also changing textures, the virtual try-on, a lot of stuff. So here we show the results of the denoising, this diffusion on the novel views. So on the kind of right column is the primitives we learned. Here is our texture mesh. And we can also do this novel pose. You can kind of animate your 3D avatars, right? So you find that, okay, so it's a pretty good way, very efficient, a fit for network. However, the texture quality is not so good because if you want a very realistic avatars with 3D humans, sometimes you just want it's in like 1K is a resolution. So that's why we're also working on another type of different model. It's called structure LDM. So it's like the 2D SD, stable diffusion, except that we have the inner 3D structures on this latent space. So previously, the latent space is just 1D, right? You use an autoencoder, you encode this 1D embeddings. However, if you use this 1D embeddings, you have discard some of the spatial and fine-grained information, right? So here we try to use the structured latent, that is 2D or even 3D. We have all these UVs on the latent space so that we can learn the 3D humans on it. So here is the results. You can see some of the textures are much better. And it can even tries to predict different dress, different skin colors, and also you can see the back view is also pretty good. So note that this work is just learned on like the limited amount of images, not learned from like 3D ground truth. And we can also do something interesting. Is we can doing this mixing. That is, I want to take the body of one person and mix it with the clothing from that person or face with the third. So it's called like compositional generation. So in this case, we show that our latent is pretty smooth. You can do this interpolation, composition, and creating novel things on it. So here is more results. You can see a different style, different clothing, different pose can be good. And building on this work, we also build an interface, right? Just using like text, like prompt or this unconditioned is not enough. So humans always want more controls, right? Like the sketch, like we have some like mask, like this drag, right? So we propose this fashion engine that is we can doing this multimodal editing. So here shows one of the cases. We can first generate 3 humans. Note that it's a real-time demo, right? So we can run real-time on the GPUs. We can use a sketch to generate the sleeve. You can also choose different poses as you like. Then you can choose the view. You can also change the shape. So because we have a structure latent, so it's very nice to disentangle all the different properties. You can do that. You can even do the animations again. You can give in some pose sequences. And besides that, we can also do this text-based generation. Like lady wears blue dress, then you can try to generate. We have some galleries. You can also choose one of the reference. Then you can change in this pure color and also changing her arm to sleeveless, right? So that's all real time, right? Thanks to the underlying 3D structure out there. Okay, so I will skip this part. And then we're also starting to like try to leverage the power of Gaussian splatting, right? So previous models were working on structured human representation plus some nerve things. And last year, Gaussian splatting came out. It's a very efficient method. So we also tried the Gaussian. So it's also will be presented in CVPR by Xian this year. The key idea is the same. That is, we also incorporate the human priors like skeleton, like depth inside. So that is baked into the SDS score distillation. So after that, you can generate like something like, so it's all tech-driven generation. So this one can also generate very high resolution results, can be readily used in games. So you can see here's comparisons with other works like Dream Gaussian, like TADA with Dream humans. We achieved the best like the qualities in terms of geometry and textures. So we can also do in some of the animations using the AMS datasets. And finally, you see, we are not just content with satisfied with just 3D. Sometimes we want to go into the like 4D. However, in the 4D, these scenarios, there's like different like sports, dancing, they have rapid movements. So it's very hard to capture all the like the clothing deformations, like the wrinkles on that, right? So here we propose another work, it's called thermal. So that is, we should just directly model a surface instead of the voxels or other representations, right? So we advocate using the surface as well as another is physics-based encoding. So that is, we can do in the 4D capture quite well. So you can like capture this person, then place it other places to do this free view renderings out there. And finally is that how to do the animation. So previously our animation is based on predefined sequences, right? So you have some sequence you capture like from some like artist or from some performer. So here we show that you can also leverage these large language models to do that. So for example, you have some description like this one. So how to do the stage 1, stage 2, stage 4. So how to move the limb, how to move your pelvis. You combine them together with some transformers. So I'll skip the details. It's a diffusion transformer. And finally, you can generate something like this, right? Of course, the avatars can be changed to something we have synthesized. So here's the movements. You can control to each of the part, right? It's not holistic control, it's part level, very fine-grained control of the human body motions. Okay, so after talking about the first part on the avatars, I think I will go to the object. So object is more complex because our daily objects are like 200 categories to 500 categories, something like that. For humans, we can always leverage the file, but for objects, it's always hard. The first thing we do is we build a data set. It's called Omniverse 3D. So compare with the Objectverse. So this data set is purely scan, real scan, right? So Objectverse, many of the objects are from the CAD models. So this one, we actually manually scanned 6K high quality 3D models. So now it's still growing. And we have 200 categories. Now we have grown to 500 categories. We have included like texture mesh, point cloud, the videos and model images inside. So you can use the dataset for a lot of different applications. So you can see the comparisons of ours to the other personally used like ShapeNet, ModelNet, Observers, something like that. Of course, due to the fact we're scanned from the real world, it's naturally a long tail distributions. And the categories here also have some overlap with the popular 2D datasets like COCO, ImageNet, so that you can also study the transfer of the 2D knowledge to the 3D domains. So now we are also trying to add in the very fine-grained this caption description for each of the samples inside. For example, the third one is a glass case. So the appearance is overall it's purple. The box features the pink Linabelle on the surface, wearing a dark purple flower and blue eyes. So I think learn from the lessons from Darley or Sora, this kind of very fine-grained caption is essential for generation, right? So we have provided these kind of captions for the academic communities to study the 3D generations. Of course, based on dataset, we have trained our own model. We have trained the 3D diffusion transformers on the large vocabularies. Now we can generate like 500 categories out there using this single diffusion model. So after that, of course, we have to handle the efficiency. We also propose another work, it's called VertSurf, very fast objects reconstruction. The previous people use like news. It's a neural service. It takes like hours And our work is only like 5 minutes. You can scan in like 3 or 4 views. You can get very high quality 3D objects inside. You can also add in textures on it so that you can have your daily objects transported to your digital world, right? So within 5 minutes. So that's pretty fast. So I think the last part, the thing is the most complex one, and I think that's also most interesting ones. We spend a lot of like recent efforts on this part. One of the work is last year. It's called Text Light. I think it's in South Asia. We want to generate some 3D environment from just text, right? So this year you have the Vision Pro, you have the AR, VR glass, but we don't have enough 3D environments out there, right? So how about we just generate from text, such as this brown wooden dock on lake surrounded by green trees during daytime. So if just given this text prompt, we can generate a 4K resolution, this image. So what's better, we have this HDR, that is, we have that high dynamic range so that you can put novel things inside, you can do relighting, this reflectance modelings. We also have built a Blender add-on, so you can also try inside Blender. So here is some of the results. You can see left is the prompt, this brown wooden floor with white wall. For this one, empty parking lot during daytime, right? Essentially, you can generate a lot of things, indoor, outdoor, out there. We also show our real-time demos here. For example, you input a prompt, the brown wooden floor with white wall. Then we'll generate this one. And of course, you can put new things inside. Here is the renderers. You can first put, I think that's the standard objects in the graphics, right? You can see all the reflectance, the lighting, if the light on the wall, that's pretty realistic. And you can do the renders out there. And finally, you can also take this VR view of these environments. So even though I think the work has achieved very good performance, so one drawback is that you can't walk around because it's a panorama, right? You can just like see around, but you can just go because it's not true 3D. So after this work, we have building another one. It's called Scene Dreamer that want to build a true 3D scene generation that is also unbounded, that you can automatically grow the whole things out there. So here, our idea is to leverage in the wild 2D image collections because it's very hard to collect 3D scene ground truths, right? To collect 3D objects is already pretty hard. Collect 3D things is even harder. So we just leverage all the in the wild 2D image collections and train. Here is actually GAN models. You can see we can have a very good generations of the outdoor views. Like you can see have multi-view consistent. It's also well-defined geometries. You can sample different styles, daytime, sunset, something like that, right? So with this model, we have the true 3D. So it's just like game engine. You can put like avatars inside, objects inside. So now we can achieve like infinite 3D world growing as you like go to the different places. And we can also doing the sampling of different styles of the things. You can also choose different camera trajectories. If you want a drone view, side view, you can choose anything you want, right? It's free camera trajectories. So for this work, it's mainly working on this like the natural things. So how about the urban or city things? So here we have City Dreamer. It's also going to apply the same idea to the 3D city generations. Of course, this work will also be presented in CVPR this year. So the major difference is that we can leverage the city layout. Because a lot of the urban cities, they have regular layouts that can be learned the patterns, and we leverage layouts to generate the whole cities out there. So I think here's demos. You can first choose the layouts. You can, of course, editing the layouts out there. And you can choose the rendering angles, generate first the geometries out there. Then you have the renderers for the textures. So for this one, we can also import into UE, into Unreal Engine. If we import this one into Unreal Engine, you actually try to build your dream cities, right? So here's the results that is put into UE. We do the render of the lighting. Then you can have virtually abundant 3D cities out there. Of course, now we also have ongoing work that is try to speed up. So even though this work is have a very high quality, it takes hours to render. It's pretty slow. So we're also trying to do this Gaussian splitting to replace the nerve, so that we can achieve like near real time. It's 10 FPS rendering out there. So it's still ongoing work. So we'll try to make the city generation real time. And finally, of course, we also try to model the indoor scenes out there. So it's called Perf. So this one is given one panorama image. You can either use a camera or using the one we have synthesized. Then we can generate a 3D indoor scenes inside. So here is some results. So input is just one panorama, and output is the 3D scenes you can work around. And here is the real life demo, right? You can control on your laptop. It's just run also real time. So here is the results. If we combine our text to 2D panorama, text to light with the perf, we can work around the kitchen, the bathroom, and also more. You can work around the living room with one TV out there, a large bedroom, and also more. So this one is colorful beds and kitchen, right? So I think this has a lot of potentials for interior design and also these VR tours. And this work, I think, is collaboration with Lin Jie. That is kind of very fast 3D scene reconstruction. So we can use a mobile phone to take a footage. Then we can construct the large-scale 3D nerve. We also have tested on the N2, the campus. You can see it's our own taken once. So geometries, this kind of recovered depths are good, right? So after talking about this avatar object scenes, finally, I want to talk about some of our very recent efforts to build foundation models. I try to unify them. Can we collect large-scale data sets and truly build some tools that is useful for humans to do some creation, right? So previous one, they are just on specific domains, on avatars, object with scenes. You have to leverage all the priors. How about the foundation models out there? So one of them, the first one is this year, is collaboration with Meta. So it's called Your Hand. That is, we're trying to learn from large-scale light stage data to do the kind of universal model for the reliable hand. So it's very kind of essential for the VR applications, right? So we learn a universal player here, and then you can put your hand in different environments, right? We have 3D environments, you have your hand, then you can put your hand in different environments. So it's good because we only need the one phone scan. We have tested you just by using one iPhone to take one very short footage, and you can put your hand everywhere, right? So that's one foundation model for the hand, right? It's called universal models for reliable hand. And here's more demos out there. I think this one you can see in different environments, the lighting, the reflectance, and also the interaction between different fingers. They have captured quite well. So here is more on this last two on the indoor, and first and the second is the outdoor. So after that, we try to build some models for like the motion generations, right? So previously, I've seen different people working on different subfield of motion generation. So some people working on text to motion, right? Give it some prompt, like synthesize some sequence. Some people working on this music to dance, give a music, synthesize some dancing, 3D dancing out there. Some people working on this talking face, 3D talking face with 3D like gesture, code-based gesture generations. So we're thinking of all these tasks, they are human-centric. And they're working on different domains using different data. So how about we unify them using one single model to tackle all the different tasks that relates to human motion, right? It's called like large motion models. So we find that just using one single model, you can achieve pretty good performance across the kind of 8 or 9 different tasks out there. So the key, of course, is on the data, right? To build a foundation model, the key is always on the data. So here we show that how we unify the 15 or 20 data sets into unified formats so that we can train a foundation model on all these data, try to learn transferable representations. So for the architecture, it's straightforward. We use transfer kind of MOE, mixture of experts, so that during inference, we can have efficiency out there. So due to time, so this one, I will just quickly show the results. So we have text control. You can do the text control there, or you can do in the speech controls. I think here it's not moving. You can also learn from the videos, mimic the video, right? and you can also have some music out there, right? So for this one, if you're interested, you can check out the website. And we have another work that is on just on the video mimic. So this task, I think, is the most widely used. Everyone wants to create your own avatars using just one video, right? So how about just using one video and do the mocap instead of building the live stage, the multi-view capture system? So that's the one we call the simplex. That is the motion capture foundation models. I think the largest model for now, our release version is 1B, but now we're building like larger models. So given just one input image, like the left one, so we can extract the 3D motions, the shape inputs, and we target it to another either avatars or characters out there. You can also try other like sports style videos. So the idea is pretty simple. Of course, the key is also on the data. We just use a very straightforward like the transformers to do it. Okay, so for this part, I think I will just skip. So we find that on the 3D generation, 3D humans also scaling law also holds. More data, larger model, the performance is already better. I will skip. So for this one, we also give you some lessons how to use synthetic data, right? So for humans, we don't want to use real human data because of the privacy concerns, right? So here we show that synthetic data is very effective. You can use that to train foundation models. And finally, we show that you can also do your own. It's recently the kind of the startup called Wonder Studio has been acquired, right? They also have this function that is you replace some of the characters in the movies. We show that you can do that using a simplex. You can like create your own La La Land. Right here is the two characters. Can replace the motions to the other two. Yeah. Okay, so to timeline, I will just stop here. And thank you. That's all for my talk. Yeah.
Yeah, due to time limit, we will have one quick question from audience. That's where I think maybe I have one question.
Yeah.
For the human-related work. Did you do any special things in data or network side to make sure the foundation human model are not biased to people from certain location or certain skin tone? I think people always complain about that.
Yeah.
Yeah, can you introduce something about that?
Yeah, of course. We have done a lot of things on the data side. That is, we find that a lot of the data set, they are created either in Europe or in like US. So it's not applicable to like Asian people. That's also enlarged that one, also try to diverse the distributions to do that.
Yeah, so more data more important.
Yeah,
okay.
Yeah.
Okay.
Yeah, so for these human foundation models, it's not so like computation extensive like the general 2D. So you just need like maybe 32 to 64 GPUs to train. Yeah. So.
Okay. Yeah, okay. Let's stop here and we set
let's do this one. Do you need the data or do you post it? I have no idea. Okay, now. Do you know what to do at this point? Okay. Do you desperately need presenter mode? Quite like presenter mode, yes, please. Okay. Does anybody know Max? Hold on. What's happening? They want us to change it, shit, right? And it's unclear how you do that with presenter mode. We're not Zoom experts, sorry. No, it's not on.
Not mic
Not mic
expert
expert
either.
either. All right, I think we're there. My mind is actually blown by how impressive that was. So quick round of applause for Jimmy. Okay, hi everyone, I'm Jack, and alongside Jimmy, who you've all seen in action for the last few minutes. We're going to be presenting Generative Interactive Environments, which is our project learning an action controllable video model without action labels. So this talk is going to be focused on our paper that came out in February this year. It's going to be presented as an oral at ICML this summer, and it was an amazing collaborative effort from all these people you see on the screen, even including the pets you'll see later on. So for the bit of context and motivation, there's been a lot of excitement recently about the incredible capabilities of LLMs. Obviously, we're at the Computer Vision conference, so maybe we're not as excited as everyone else about this. But as a result, many people in that area of research have been extrapolating this further and saying that we're close to achieving some kind of AGI via scaling LLMs. It's certainly possible that this could be true for some kind of virtual agent. However, if we want agents that can interact in the real world and have some kind of embodiment, then we don't think this is going to be enough. Our key claim that inspired this work is that we need a sufficiently rich and diverse environment to make it possible for our agents to collect their own experiences and become some kind of embodied AGI. So first, we're going to begin with a little bit of a history for why we think this is the case. So recall back in the stone ages of AI research in 2013, when researchers from DeepMind got access to the Atari environments only a year or so earlier, and were able to get human-level agents in all of these different Atari games. And at the time, this is pretty remarkable because this is the first time that we could see agents really playing these games that humans even find somewhat challenging sometimes, and actually discover completely new strategies. After this has been pretty rapid progress. So only a couple of years later, given access to Go simulation, then also from DeepMind, we're able to get superhuman Go agents. And despite this being nearly 10 years ago, it's still pretty mind-blowing that a game that was played for thousands of years by some pretty intelligent people was able to not only be solved and conquered by an AI agent, but that same agent could then teach us humans completely new things that we didn't know about this area before, and actually augment our intelligence and really advance our capabilities. However, this isn't really AGI or some generalist agent. This is an agent that can solve specific individual environments. And so we really like this idea of this paper from Morris et al. That came out earlier in the year that kind of factorizes the capabilities of AI agents in two different dimensions. So on the rows, what we have is different performance levels, and on the columns, we have different breadth of agents. So what we see with the RL agents that we just showed is that they're really good in the narrow scope at getting superhuman performance. So we see with AlphaZero, it's better than any human on the planet, and it actually can teach us completely new things, but only in Go. And AlphaZero could do chess and shogi as well, but that's not the point. On the flip side, we see things like ChatGPT that are very general and have this amazing breadth of knowledge, but they're not really, I mean, it's maybe competent, but not really. They're pretty primitive at most things, but they're good at a lot of things. So our key claim to achieve the bottom right is that if we have a sufficiently rich and complex environment, that there may be the same technologies that got us AlphaZero and back in the day DQN could get us a generalist embodied agent that can discover completely new things for any visual environment, which is a bit more exciting to us than anything else that we've seen so far. So how can we get this environment? And that's the main motivation for this project. Well, making it a bit more relevant for the community in here, it's pretty clear that there's been a lot of progress in video generation. It's having a bit of a moment. And I think progress has been so rapid that since we made this slide a week ago, there's two new amazing models that came out. So shout out to the teams at Runway and Luma for the last week, because it's just mind-blowing to see all this progress in this area. There's actually, I think, Gen 2 in the bottom left. And our colleagues at GDM with VO. So now, the key goal of our project is to make use of generative video models and train the next generation of embodied agents. And when we started this project, it was quite a novel idea. It took a lot of convincing people back in 2022, 2023. But it's becoming increasingly clear that there's a lot of potential in this space. And these models really do have some general knowledge of the world. With continued scaling, they could become realistic simulators for agents. However, many of the text to video models that are currently available are only controllable at a very high level. So you might be able to describe something in text and see a whole temporally extended sequence of actions. But what you can't do is control at a low level and actually learn on the fly how to behave in an environment and really get some sense of some grounding for an agent. On the flip side, there's this other area of research, typically in the RL space, of world models, where we do have action-labeled data, and we can learn a world model, like if you've seen Dreamer v3, that can then allow us to simulate these environments and perform long horizon trajectories in these learned world models. But they've never really been scaled because these models require action-labeled data, which we don't have at internet scale. So I guess I should have been pressing next, but you get the idea. This is the problem we're trying to solve. So in our project, we want to make use of the vast amounts of unlabeled videos on the internet. We also want to train a video generative model that allows for action level control. And these two things are often come at a bit of a paradox. And so what we propose to do in Genie is to learn a generative interactive environment purely from videos that's playable by both humans and AI agents. And the main way we plan to do this is using latent actions. So these are learned in a fully unsupervised manner, and intuitively, they kind of correspond to clustering the possibilities from a given frame over the distribution of next possible frames. I'll now hand over to Jimmy, the hero of Zoom, to once again go through the architecture and some of our results.
Thank you, Jack. I'm Jimmy, the hero of Zoom, I guess. And I will be talking about our model. Okay, so the Genie model is made up of 3 different components, and our model takes in 16 frames of video. So first, we have the video tokenizer, which takes in the entire video and discretizes it into video token Z. And then at the same time, we have this latent action model, which is the yellow block down at the bottom, that again takes the same video as input and extracts latent actions, where each one of the latent action should denote the transition between 2 consecutive frames in the video. And then finally, we have our dynamics model, which is our generative model. It's a masked model that takes in the video tokens and the latent actions and generate future frames. All of our modeling components use this one architecture, which we refer to as spatial temporal transformer. The spatial temporal transformer consists of L spatial temporal blocks, where each of these blocks contain a spatial layer, a temporal layer, and a feed-forward layer. And here, each of the color represent a single self-attention map. So at the bottom, we have our spatial layer. It attends over only the spatial tokens from within a single frame of the video. And then the temporal attend to the same token across the T time steps, in our case, 16 time steps. Okay, now let's have a look at each individual component of our model in a bit more detail. So first is the video tokenizer. The tokenizer is a VQ-VAE that takes in 16 frames of input video, compresses it through a VQ layer into discrete tokens, and then decode to reconstruct the tokens back to 16 frames of raw pixels. So we pre-train this video tokenizer in using our data set, and then it's frozen while we train the other 2 modeling components, which is coming up now. So now we're moving on to our latent action model, which is arguably the most interesting modeling component in Genie. So the latent action model takes in the video as input, and it extracts latent action. So the latent action, again, the latent action model take on this encoder-decoder structure and also has a VQ layer in the bottleneck to have discrete latent action. So let's have a look at the encoder first. The encoder takes in the entire history as well as the future frame as input, and it generates this latent action that encodes the transition between the history and the future frame. So here we limit the latent actions to take on a values only. So in the analogy of a video game, it would mean that at any given time, there's only a different player action that you can take. And note that the latent actions here are learned in a fully unsupervised way. So we don't provide the model with any action label. Now, how do we do that? So that's where the decoder comes in. The decoder, again, takes in the entire history as input. But in this case, instead of the future frame, it takes in the latent action that was generated by the encoder as input. And its task is to predict the future frame. So this means that the encoder, while generating this latent action, has to squeeze the most important information about the transition between the history and the future frame into this tiny bottleneck. In order for the decoder to then successfully take the history and the latent action to generate the future frame. And in an unsupervised learning setting, this means that the model typically would encode the factor that is the most causally relevant to the transition in the video, which is typically character movement. And then the decoder is also used only for training and discarded at inference time, and also while we train the dynamics model. And speaking of the dynamics model, we use a mask-it model, and we mask out 75% of the input tokens during train time. So the model takes in both discrete tokens as well as the latent actions generated by the latent action model as input, and generate the video tokens of current frame. Okay, so now that we've introduced all of our modeling components, let's have a look at what happens at test time, or in other words, how can the user interact with our model? So at inference time, we provide the model with a prompt image. So this image then gets encoded by our tokenizer into discrete tokens Z1. And then where do we get the latent action? So there are two options. One is that we can infer it from ground truth frame using the latent action model, where we give the model the prompting frame and the future frame and ask it to annotate the latent action. So this is useful when we want to generate a video that is completely faithful to the ground truth video, and especially useful when we're evaluating quantitative metrics such as FVD or PSNR. But option 2 is kind of where it gets interesting. That is, the user can actually choose the latent action. And as long as the user is choosing the latent action within the range of 0 and 8, which is the number of latent action that our model is allowed to have. And then we give the mask-it decoder the latent action as well as the token, and it predicts the token for the next frame. And then once we get this next frame token, we can plug this back into the input of the mask-it model, choose another latent action, and generate another frame. And we can keep going this way until the model has generated an entire video. So Genie was trained on a data set of 300,000 hours of publicly available internet gameplay videos of 2D platformer games. We found that it was important to filter the data by quality. So we trained a classifier on 10,000 hand-labeled examples, and then eventually this leaves us with a data set of 30,000 hours of high-quality video gameplay. And before training our final model, we conducted a scaling analysis, which showed that our model's performance increased with model size and also batch size. And this is what led us to our final Genie model, which contains 11 billion parameters with a batch size of 512, which produces a foundation world model of 2D interactive environments. Okay, now enough of the boring stuff. Let's have a look at the results. So this is a quick overview of the generation from our model. So our model is able to take in a prompting frame and generate vastly different trajectories. And these are prompting images generated by text-to-image model, or our sketches, or even real-world images in some cases. And that's what sets Genie apart from video generation models, is that it introduces fine-grained frame-by-frame interactability. So the first property of the model that I want to talk about here is that our model can generate diverse trajectory from the same starting frame. So what's happening here is that we're giving our model this prompt image that is generated from a text-to-image model. And then we allow 4 different users to select the latent actions that they want to see on a frame-by-frame basis to generate these videos. And we see that with different latent action sequences, the model generates completely different trajectories. So if anything, this tells us that the latent actions do mean something to the model. Now, how much do they mean to the model? Well, here's another property of the model that we're excited by, which is that the learned latent action are consistent across multiple prompting frames. So to demonstrate this, we take 4 different prompting image that are again generated by text-to-image models and give the model the same latent action sequence to generate these 4 videos. And we can see that the generated videos roughly depict the same motion. So this tells us that with the same latent action sequence, even with different prompts, the model can generate similar character behavior. And this is particularly impressive that our model can exhibit this behavior, especially when it's trained in a fully unsupervised way. And again, this is like hammering in the point that Jack was making in the first place, which is that we don't really need all of these inductive biases like action label, object detection, or anything like that to have this sort of disentanglement in our latent action space. All we need is scaling unsupervised learning, and that's enough to learn a world model. Now we have shown that our model meets the criteria of a world model in that we're able to generate these counterfactual trajectories and we have a consistent latent action space across different environments. However, what we didn't anticipate was the huge potential of this model for creativity. And these are sketches created by people working on the project. Richie, in the middle, it's Jeff Kloon's kid, and then Ashley made the drawing on the left-hand side. And we're able to bring them to life with our model. So this is absolutely wild to us because the model was trained solely on internet scale 2D platformer data, and it has never seen any data like this, but we're still able to do things like control the character to do things like climbing the ladder or moving the football player to the left and things like that. And results like these have really helped us open our eyes to the kind of creativity that Genie could enable. And we also went a little bit even crazier and tried out super out of distribution real world images that are completely unlike anything the model has seen. So that's Jack's dog Doris, and then there's Tim's figurine, and then Ashley's pizza slice. And we're again able to interact with these environments even though they're very different from anything the model would have seen. Another exciting capability of our model is that it can generate parallax, demonstrating its 3D understanding capabilities. And this is just a model that's trained on 2D platformers. So just imagine what a model that's actually trained on real world data can do. And these are parallaxes that are also generated with the same latent action sequence as denoted at the bottom, and therefore depicting roughly the same movement. One step further into the real world, we also trained a model on robotics data. So this is a separate model. It's much smaller with just 2 billion parameters, and it's trained on a relatively small data set. But we're already seeing properties like, again, consistent behavior across different prompting frames. And then on the left-hand side, we show an example of the model simulating deformable objects. Okay, now we're passing it back to Jack to talk about the future.
Okay, hi again. I think the main thing we want to emphasize with this is that this is the first action controllable world model trained from internet scale data without action labels. And so this is hopefully, if we do our jobs right, the worst it's ever going to be. And so we think there's quite a few potential possibilities in the next few years. If we think that, it's been 10 years since DQN, in 10 years more time, where we think this could go, or maybe less. So first, going back to our original motivation, we think Genie prevents a clear path to generating unlimited environments we would need for training embodied AGI. For a more formal write-up about this, Jimmy, myself, and some others in the open-endedness team at Google DeepMind have a position paper at ICML, which is also going to be presented as an oral, which kind of shows you how we think these all things combine with basically open-ended learning and generating infinite possible environments. But that's not for today, but feel free to check it out. And we think this really could be the future for training agents, especially visual embodied agents. But don't just take our word for it, because I don't know if he's in the crowd, but Jim Fan agrees, and he's, I think, also a world-leading expert in this area. Rather surprisingly, though, maybe even the more exciting angle, and I wouldn't have said this a year ago, is the impact for creativity. So even with this first version, the team had a lot of fun playing with the model, which already enables people such as young children to create their own virtual worlds, step into them and play them. And I think we're really just scratching the surface of what could be possible here. And so here's some additional quotes and ideas. I think this space could really go in unexpected directions in the next few years. And models like Genie could enable completely new applications and new ideas and creativity that we haven't even thought of. And the final thing that we wanted to comment on is that it wasn't too long ago we were GPU poor students who would have thought, yeah, reasonably cool, but this doesn't relate to me. We do have a small scale reproducible case study in our paper. And I'm chatting with some students who are hopefully going to actually open source something in the next few weeks. That will be 100 million parameter model. It trains on a single GPU for less than a week. That gets you these latent actions, so each row being a different one in the coin run environment. It's not the full model, but it's something. Okay. So hopefully this can let people do some research in this area and at least kind of like contribute, I think, to what could be something really exciting in the next few years. So yeah, that's a wrap. Thank you all for your time. Sorry about the tech difficulties.
talking about curating the data, so filtering high quality. How do you define the quality of these kinds of videos in this domain?
Thank you for the great question. I would say the data quality at this point is mostly vibe-based, but there are also a set of criteria that we're using for things like, because we're just taking internet video gameplay, the things that we look out for are things like, does the video contain menu? Is there a streamer face in the video? Is the video of high quality in terms of like resolution? Does it feature valid video gameplay and things like that? And we hand labeled 10,000 videos just based on these criteria, just by their quality of like, based on these criteria, is it like on a scale of 1 to 5? Is it a 5 or is it a 1? Does that answer your question? Cool.
Hi, so you talked about kind of scaling this model to further show its potential. And obviously, if you just scale on platformer games, then that's nowhere close to embodying AGI. So how do you plan to expand to other types of actions? And how do you even begin to define an action once you go out of a platformer game?
There are lots of options. This work was largely from last year. So to some extent, we have already tried to do this a little bit. There's lots of possibilities, right? So firstly, we do have some action labels for some environments and worlds. We can use things like large vision language models, maybe to annotate some data. We can also just scale this current approach. The current approach we did was the simplest thing we could think of last year, and we were quite surprised it worked. There were a bunch of other ideas. I'm not sure how much detail I can go into these, especially in a larger forum, but if you want to get in touch, we could chat more maybe offline. Yeah.
At the back of the white shirt.
When you say surprisingly consistent, you kind of showed it for the language model. Do you have numbers or a graph or a sense, especially like when you're dealing with unsupervised data, probably it's difficult to kind of get a sense of just how accurate that is?
Yeah, these are really good questions. So the reason that we say surprising is because I guess having done a lot of research in the space of unsupervised learning, we know that disentangled representation is really difficult to acquire. And then once we tried this model on large scale data with like scaling the model size, scaling the batch size as well, it just sort of naturally fell out of the model. So that's why we use the word surprising, is that it's not something that we observed in our GPU poor days. Sorry, what was the actual, is there like a quantitative metric that we use to look into? Yeah, so there are a few metrics that we do use. I don't think we included this in our publication just because none of these metrics are complete because we don't have access to the real action of these, to ground truth action of these videos. So a lot of these things are like how consistent the latent action is if we like plug the generated video back into the latent action model to see like if they line up, things like that. But we mostly do like a lot of human evaluation by just like looking at the video across multiple prompting frames to see if they're consistent. And in this case, they are. So yeah.
We have time for one more question, please.
Have you experimented replacing action labels with action embeddings so that you have more variety on what would happen in the video?
We actually do use action embedding as input to our dynamics model. So because the latent action model contains a VQ layer, there's like the actual discrete latent action tokens. And then there are also latent action embedding. And when we condition our dynamics model, we use the latent action embeddings instead of the VQ tokens. If we use the latent action embeddings as the actual control, as you can imagine, the dimensionality just increases dramatically. And it will make the model much harder to control. Because right now we just have 8 different actions and the user can just like choose which action they want to pick. If we use embeddings, it'll be much harder. I guess you can imagine like interpolation, like a sliding scale for each dimension, but that's something that we left to future work or to you.
On point run.
Yeah.
Okay, let's do this.
Okay.
Myself. Whoops. That's good. Cool. Yeah, thank you. Yeah, thanks for the intro. Actually, I did not yet finish the PhD. But that might happen. In the meantime, we're doing some diffusion and distillation research, which I want to talk about. And yeah, this talk has the title "Diffusion Distillation Done." Kind of to imply there's a lot going on in diffusion and in distillation. I'll give a brief overview over that, but then the question is, where do we go from there? What are the next difficult topics that where it's worth spending some time and research on? But actually, I just want to give a quick shout out to this workshop because I think it actually really contributed to the progress of generative AI in general. So 4 years ago, the samples that we got out of our models, which were at the time conditional normalizing flows, they looked like this. You really had to cherry pick to get something like this out of it. It was like strongly conditioned on semantic layouts, 128 by 128 pixels. And now 4 years later, we can get something like this, which is a sample from a text-to-image model, which shows a lot of complexity, a lot of detail. It's really interesting that you can dive into these worlds that the models are able to generate. For example, we can look at these people here on the right, shopping something at the counter, people in the middle walking along the street. What's going on in this window over there? Lots of potions or bottles being sold. We can think about what these people at the cafe are talking about, and then actually what is this pig doing over there? So there's so much going on, and it's really impressive what complexity these models can capture nowadays, and it's only something that is getting stronger and stronger. So this is a pretty famous video from the OpenAI Sora announcement, where this couple is walking through Tokyo, I think, and it's the same here, right? There's cars driving in the background on the road, other people walking, interacting with each other, different stores on the side popping up. And then just the quality of the stuff is growing quite rapidly. So this is from today's announcement of Gen 3 by Runway ML. And this sample I find pretty impressive. The prompt for this is a middle-aged, sad, bald man becomes happy as a wig of curly hair and sunglasses falls suddenly on his head. And it just follows this prompt really well, while the quality is super high. So it's really good stuff. One more question is, the answer is kind of obvious. How did we get there? A part of it is obviously scaling. So these architectures and the algorithms that we use to train the models are very scalable, and we have a lot of data available, a lot of images, a lot of videos. So it's kind of a perfect fit. On the left, just for visualization, the classic scaling plot from the GPT-3 paper. On the right, a bit more relevant to the stuff that we're actually doing here, is from the diffusion transformer paper. A plot that demonstrates that we can really increase sample quality by increasing the number of flops, the amount of compute that goes into training of these models. And we can either do this by increasing the model size, or by increasing the sequence length, or by doing both. Yeah, and this just works very well. And then one question you might ask yourself is, okay, I mean, that seems to work. So are we done with that? And if you have a lot of compute and a lot of money available, that can be a completely reasonable answer to further scale these models up, because it doesn't seem like we are at a limit, at least for these kind of image and video models yet. So it can be an answer, but on the other hand, a lot of institutions don't have infinite amount of money or compute available. And even if you have, you still want to make sure that you actually don't waste a lot on something inefficient. So there's some research to be done on finding the most efficient algorithm that gives you the lowest loss, let's say, for a given compute budget. And on the other hand, if you grow these models, the inference becomes a bit more tedious. So for an image generation model, it's typically around the order of seconds to generate a 1 megapixel image with the state-of-the-art model. And for video generation, it's a bit less sure, but so we don't really know for Sora or for Gen 3. We do know for Luma, who released last week, and there it's, I think, 2 minutes for video generation. So yeah, it's definitely on the order of minutes. So one very interesting area of research here is to find algorithms that make the sampling more efficient and speed this up. Also, this just improves the experience when you interact with these models if you don't have to wait for minutes. And I want to talk a little bit about both because we did works in both areas. And I want to start with the first part, which is finding a more, or kind of, yeah, the best algorithm that you can then scale up to achieve the best training loss in a given amount of compute. And we did this in this paper here, Scaling Rectified Flow Transformers for High-Resolution Image Synthesis, which we published in March. And basically, the motivation for this was that back in November, we really wanted to scale up the models. But there was like this zoo of different diffusion formalisms available. It still is. Like you have classic DDPM, you have EDM, epsilon prediction, V prediction, different kinds of schedules. Some of them are very similar. Some of them are actually equivalent. But still, there's like a huge zoo. On the other hand, you have different architectures that are being used. So you have UNets, pretty popular, transformers, diffusion transformers, and mixed variants like UVITs, which is kind of a UNet that has a big transformer in the middle. So we did a study on which of the architectures is the best and which of the diffusion formalisms is the best. And to start with the diffusion formalisms, I want to give a little bit of a background because we ended up using something that is kind of new, which is called flow matching. And yeah, I'm pretty sure that you've seen this formula. This is basically just how you construct your training data for your diffusion training. So you sample some data from your training data distribution and you add noise to that. And you do that by something that's called the diffusion schedule, which is defined through these coefficients here, AT and BT. And by choosing these in certain ways, you can recover these classic formalisms like EDM, DDPM, deprediction, etc. Yeah, but one that popped up quite recently and really got traction is this formalism of flow matching, and within that special case of rectified flow, which basically just interpolates between your data and your noise. And if you plug this in, your conditional flow matching loss, then the task of your neural network is basically just to predict the difference between data and noise. And then after you've trained the model with this loss, you can basically just solve this differential equation here and for a given noise sample arrive at a sample from your data distribution. And it's actually like I'm a huge fan of this formalism because it is so simple. On this slide, you have basically everything to implement it. You have the forward process and the loss and how you sample it. It's a super simple Euler sampler. So yeah, it removes a lot of the overhead from typical diffusion formulations, and it works just as well, as we will see in a second. And yeah, I said it already, it's part of a broader family of models, this flow matching formalism. And that one is pretty cool too, because on the one hand, it is more general than classic diffusion. Diffusion is a special case of flow matching. You can recover it from it if you choose like this certain forward path that was on the top of the slide here. But you don't necessarily have to do this. You can, for example, also interpolate between data and the data and some other data distribution. For example, you can train an upscaling model by interpolating between your high resolution data and low resolution data or something like this. So it does not necessarily restrict your base distribution to a normal distribution or something like this. It's also much simpler than diffusion or diffusion formalisms that are based on something like stochastic differential equations. You don't need that. The only thing that you need to arrive at this loss is basically the continuity equation, and that's it. So yeah, I can just highly recommend to look into this literature here. These are 3 papers that kind of discovered the same thing at the same time. It's really worth to look into it and simple to implement. All right, so we added that formalism to our investigation of different diffusion formalisms. And one thing that in the past worked really well for diffusion models was to reweight the loss for the different noise scales on which the diffusion model is actually trained. So this contributed implicitly to the success of the first diffusion models like DDPM, where perceptually irrelevant noise scales were discarded during the training. So it makes the training much more efficient, and you can actually focus the training on the stuff that matters in the end for perceptual quality. And we thought it might be interesting to do the same here, because especially when you train this rectified flow formalism, at the endpoints of your trajectory, the task either becomes trivial or to predict the data mean, which is kind of simple, and the difficult stuff happens somewhere in the middle. And that's why we thought it might make sense to switch from what was standard until then, using just a uniform distribution over the time steps, to something that favors the intermediate time steps more. And we chose a certain parameterization for the distribution that we sample these from, which is the log normal distribution. And yeah, you can, by tuning the mean and the variance of this log normal distribution, you can tune how you sample your diffusion time steps. And then we investigated a bunch of hyperparameters there. yeah, as I said, we trained a few models, classic epsilon prediction on a linear schedule, EDM, cosine schedule, etc., and including the rectified flow formalism with the log and normal distribution that I was just talking about. And it turns out this actually outperforms all of the existing schedules, which is super nice because on the one hand, it's simpler. On the other hand, it works as well or better. I think there's a classic case where Occam's razor applies and you just want to switch to that. And we also see that it works particularly well for a low number of steps, like 10. All right, so that's for the formalism around the diffusion model. The other part is around the architecture. And as I said, there's kind of a bunch of different architectures like units. We actually thought a bit about how to scale units, but it's just so complicated because there's so many different hyperparameters that you can tune. So we ditched them. And then we looked at diffusion transformers and different variants of diffusion transformers like the UVIT or something where you add cross-attention layers into the model. Pretty similar to how Imagine or Stable Diffusion operate. And then something new, because we thought, okay, we have these two different modalities, text and image embeddings that the model needs to connect. And inspired by approaches in vision language models, which also use dual tower architecture, we applied that to the diffusion backbone. So what we did is separating out the weights for the text embeddings and the image embeddings, which kind of doubles the number of parameters in the model. It keeps the flops the same. And then we allowed information flow between both streams by concatenating the sequence before each attention layer. And then in the end, predict on the image tokens. And this architecture turns out to work quite well. It's kind of an inductive bias for text-to-image modeling. So I'm not 100% sure if we want to take that to the super, super large scales, but for medium scales, as we will see, it works quite well. Right, and since we knew, okay, this architecture works well, and the formalism works well, we were ready to scale. Then we trained a bunch of models between 800 million and 8 billion parameters. And thought a bit about how can we evaluate these models and compare them. And since we know there's the scaling laws, which are pretty famous in language modeling, and there was some early indication of similar scaling in the scaling behavior in diffusion models, that we also wanted to investigate this in a bit more depth. And one thing that was done before was to train these models, then sample from them and evaluate some metrics on the samples. But it turns out that you actually don't need to do that, and you can directly look at the validation loss. So the validation loss is something that you get from the model by just a simple forward pass. You don't need to actually sample, which is kind of a tedious process when you're actually training a model. And how did we do that? We excluded the endpoints of the trajectory because they're pretty uninformative. And then to get a clean loss signal, always evaluated at the same noise levels, something we call the stratified validation loss. And then you see the different loss curves here for the different model sizes. Looks like a pretty clean scaling trend. And then a nice feature here is that this validation loss actually is a very strong predictor of model performance. So it correlates very well with metrics that you take after sampling, like this automatic gen eval metric here on the left. But we also did a user study where we compared these different models and had the outputs rated by humans, and we see the same correlation. So this is actually pretty cool because it tells us we don't have to sample the model to get an idea about their performance, which is true when we evaluate in the same latent space with the same noise schedule, etc. It becomes a bit more difficult if we don't do that. Right, and then one other insight which we applied after training was that direct reference optimization, which was proposed in language modeling, and also applied to diffusion models like SDXL before, works really well to further improve the quality and to actually align the model with what users want from it. So both for the smaller models and the larger models. This worked really well and improved both the prompt alignment and the image quality. And I guess the more interesting stuff is to actually look at the outputs. As a nice side effect, this approach also very much improved over the previous text rendering abilities of these models, and this seems to be working much more robust now. And you can see that it captures a lot of different styles, complex scenes. It does the writing and is able to do pretty complex composition. All right, so we have that. But now it always is a little bit of a pain to sample from these models. And actually, when you realize that your model makes mistakes, like this classic AI hand here of this guy, that becomes even more of a pain. I did that when I prepared this talk here. So I had to do another sample. The laptop is still floating in the air, which is not ideal, but okay, let's go with it. I think the point is that, yeah, just inference is kind of slow, especially when you have large models. And this motivates this other line of research, which is distillation. And there's a bunch of distillation research going on. We kind of have specialized on something that we call adversarial diffusion distillation. And our journey into this basically started with a failure. So we have some prior knowledge on GAN training. And we thought, okay, we want to get like a super fast model and try to scale up previous approaches for text-to-image GANs and just see where we could get. And we spent a lot of time, actually too much compute on it. And yeah, the results are okay-ish for text-to-image model, but really not state-of-the-art and not good. The quality is kind of low. These are 4 samples from this GAN model. And you also see that it's very mode collapsed. So the face of this teddy bear here looks kind of the same across all samples. Another sample here with one of our favorite testing prompts, cinematic shot of a Professor Sloth wearing tuxedo at a barbecue party. Same problem. The face, first of all, does not look really nice, and it is kind of collapsed. So we looked into other methods. We gave up on the pure GAN approach. One of them is this latent consistency models. This one is applied to Stable Diffusion XL. And then you see, okay, the structure and the diversity is actually pretty good already if you run this in a single step. The problem is the image quality is not there. It doesn't look like really crisp, right? But if you zoom out and, I don't know, look at this for a while, you just think, okay, it just needs a little push to the real image manifold, and then it might actually be okay. What was our motivation to do what we did before is basically just apply, in addition to the distillation loss, an adversarial loss to the model. And this adversarial loss should do exactly that, pushing the outputs to the real image manifold. And I don't want to go into too much details, but just as a high-level overview, we started from a pre-trained diffusion model, in this case, Stable Diffusion XL, and used that as a teacher and initialized the student model with it. Did a classic distillation loss where the student had to predict the teacher output, but also added a adversarial loss on top of it. The adversarial loss was implemented with the same discriminator that we used for the previous GAN model, which is based on pre-trained Dino V2 model. So it's in pixel space. I'll come back to that in a second. And yeah, if we do that, it works pretty well, actually. On the top, again, the LCM samples in one step. On the bottom, from our method, adversarial diffusion distillation in a single step. We really see that it works and the quality improves quite a bit. And why does this work? One aspect is that it reduces the output diversity quite a bit. That is pretty typically for a GAN model. So on the bottom, we see outputs from the teacher model, STXL. Then on the top, outputs of the trained student. And yeah, we see that diversity is quite a bit reduced. But image quality actually is a little bit better, which we attribute to the fact that it's also trained on real data, which can help to fix some issues that were actually in the base model. And this stuff, since it's only one step, it enables some real-time applications, which is super nice. So you cannot only do text to image, you can also do image to image based on SD-edit, where you basically prompt the model with some visual input, and then you can see in real time how it transforms that, which is a pretty cool application. And it also allows to type your prompt, and you see in real time how it renders that. But yeah, as I said before, this method, it used kind of outdated technology by operating in pixel space and these pre-trained pixel-based discriminators, which made it not really scalable, because the whole point of latent diffusion is that we don't want to go to pixel space. We had to do this in this case to train this model. But it restricted it to a resolution of 512 by 512 pixels, which is far from where state-of-the-art models operate nowadays. And since the discriminator was also operating on this fixed resolution, there was basically no way how we could go to higher resolutions. And also just this decoding step, 2 pixel space, and back propagating through it is super expensive. So we had to come up with a way that prevents this. And that's something that we did in a follow-up work that was also published in March. And we switched there from the SDXL architecture to the more recent transformer-based architecture that I talked about in the beginning. And then basically, since you don't have any pre-trained discriminative models that you can use as the backbone for your discriminator architecture, we thought, what can we actually use in the latent space that we can use as a discriminator? And one kind of intuitive thought is, okay, we can use the teacher model, the pre-trained flow or diffusion model as a discriminator as well. So that's something that we tried. We just extracted activations after each attention layer, added small learnable discriminator heads on top of that, initialized the student with the pre-trained diffusion transformer as well, and then trained that model. And that really prevents going into pixel space. It's really nice because it's the teacher, the student, and the discriminator are all the same architecture. It natively supports multi-aspects. It natively supports different modalities because everything operates on a sequence. You can, in theory, also apply this to video. And we were even able to remove the distillation objective, so this is trained with the pure adversarial objective. And the resulting model performed pretty well in the one-step regime, outperformed all the existing methods that existed at that point. And the samples could really keep up with the teacher model. So these were done in, these were done in 2 to 4 steps. It retained the ability to write, and the diversity of the outputs is still pretty high. Of course, there's a little bit of a limitation. One of them is that the text alignment, it becomes worse than that of the teacher model. All right, I have to speed up a little bit. Want to talk a little bit about video. So one very immediate application of the distillation stuff is to also apply it to video, right? But video on its own is a field of, it's rapidly growing. There's so much interest in this. So first of all, we have to improve the video models, and then we can apply the distillation on top of it. I think real-time text to video is a very interesting application. But yeah, this was done with stable video diffusion last year. Recently, you can kind of have a longer story here with the Luma model. And of course, there's so much progress in this. Runway announced Gen 3 today, which looks super nice. There's Sora, there's this thing. Yeah. I have to speed through this. Just a very brief overview. The main challenge with video is that they are massive, right? So 1 second of video corresponds to 24 frames. And that's like one of the drawbacks with previous approaches, which all try to use, or not all, but a lot of them try to use like pre-trained text-to-image models, which makes sense because you want to reuse the compute. But then you're kind of restricted in what you can actually do, and you usually end up kind of short clips. And one major insight is here that just video representations are super redundant, either if you look at these frames or at the differences, pixel differences. And that is just like a good opportunity to compress this into a simpler and lower dimensional representation. And this works pretty well. So you can train something like a video VAE on top of this. This is one that we trained with F8 compression, both spatially and temporally. It's basically able to reconstruct a video at a pretty high quality. And this is 8 times more compression, so nearly an order of magnitude compared to these previous approaches. And this gives you a representation which you can actually more feasibly apply your scaling laws. Sora used, I think, a very similar approach. There's not too much detail available, but yeah, from what they described with their latent spacetime tokens or patches, it sounds pretty similar. I don't know how much time do I have left. Done. Okay. Yeah. All right. Thank you. No, it's good.
Questions for Robin, please. He just told you all the secrets. Here.
I want to ask about the role of adversarial training, because I think that as adversarial training will now really change the trajectory of original model, as we can see that is iterable. It doesn't look like the outcomes of SD3. What do you think of the role of adversarial training?
So the question is on the role of adversarial training and why does it change the outputs? Is that right?
Yeah, styles.
The style of the outputs. Yeah, that's true. I think, and that's one thing that we wanted to fix with this approach. We only chose to operate on synthetic data, which was generated with the base model. And with the previous approach, the ADD one, we saw that we can actually improve the image quality over the base model. But this one, which is only using synthetic data, it seems like, yeah, you get some change in style. And I think if we could get the real data back in, that could mitigate that. So I think it's mostly synthetic data that is the problem here, not necessarily the adversarial training. But the nice thing about the synthetic data is that you strictly stay within the distribution of your teacher output distribution, so that kind of makes the training task a bit easier.
Multimodal diffusion transformer that you had, how critical is it to keep on having the two basically transformers replicated? Because after the first layer, shouldn't they already be in the same space?
Yeah, it's a very good question. It is not that critical. You can actually do that. So yeah, yeah. I think this dual architecture provides a nice inductive bias, but you're right. There's some experimentation to be done. How much of that you really need, and you can basically try to do no of these dual layers. Then you're at a classic DIT, or all of them. Then you're at this MMDIT, or you can, I don't know, interpolate between the two, and there seems to be some sweet spot in the middle. Actually.
All right, in the interest of time, you're going to be able to ask Robin many more questions in just a minute, but when we go to the industry panel. So for now, let's please thank Robin again. And then this take us a couple of minutes to set up. So please, check your phone, chat amongst yourselves, and then we'll be right back. You can sit there. You can sit there. Cynthia's going to sit in that.
Thanks. You dinner? Yeah. Do you have a name for the company? For your company?
Yeah.
Secret.
Two, one, two. Can you hear this at the back?
It's not like public. So.
Yeah, you can hear this.
Okay, that was small.
Okay. All right, so welcome everybody. We have two additional guests along with Robin. We have Jingwan Cynthia Yu, who is a senior director of GenAI at Adobe, working on Firefly, which is the umbrella term for all kinds of different AI technologies. And we also have Rohit Geda, who works at Meta, was one of the principal authors of Emu Video, which many of you will have seen. Just to introduce those a bit more fully, Rohit was previously a PhD student at CMU and now works in what was previously FAIR, but is now the GenAI research group within Meta. And his interests generally cover two, thanks Google Slides, two areas of research, those on how to understand multimodal data and then how to generate from that multimodal data all kinds of different video effects. For Firefly, Firefly does all kinds of different things. Now it's in many different Adobe tools, and you can use it to generate images, you can use it to generate vector graphics, you can use it within your design tools for things like poster creation. And then they also have many of the cutting edge techniques, such as using reference images for styles or for structure. Here's an example of what I think some of the new models can do, given some structure reference of the moon and some style reference of dragons or bears, produces these very nice images. And this is incredibly popular because it's in tools deployed, and I think Adobe says they now have 8 billion generations going on. Okay, so please welcome our panel today. Okay, I have 3 warm-up questions, and then we will open the floor. So, the past year has been a milestone for GenAI, all kinds of things that we've talked about today. So to each of you, what is you and your team's overall impressions of this rapid pace in AI?
Yeah, can you hear me? Yeah. It's pretty stressful, but it's also a lot of fun. I don't know, just being in the space and seeing a lot of announcements recently. It's really nice to work in it, and on the other hand, it's like you really have to, I don't know, make sure that you don't get crazy by all of the announcements. Of course, it's really nice to just see the progress that is being made. And yeah, I talked about it a little bit in this talk. Just, I don't know, comparing the state where we are today to 4 years ago, it's just such an insane progress. Yeah, so working on that and contributing to that further is nice for, what was the question for our teams? Yeah, you don't have to be on Twitter too much. I think that's one of the key insights here, because otherwise we just get crazy.
I cannot agree more that it has been very stressful, but super exciting area to work on. So I have been in this area since 2015, starting with GAN and witnessed the popularity of GAN and diffusion and diffusion transformer and so on. It's just so many amazing progress has been made. And even though I work for a big company, the team working on it really feels like a startup, and we're moving at extreme fast pace. From the beginning of the project of Firefly in about exactly 2 years ago, when the pandemic was done, and then people start to come to CVPR, and then the compute cluster became more vacant, and we just started our biggest model training. And it has been 2 years, and we released numerous versions of our foundational model and applications built on top of it. And really, it's very exciting space to be in.
Yeah, couldn't agree more. I think everything I could think of has already been said. Maybe the one different perspective I bring here could be that I'm maybe the newest to Gen AI among all of us. I mostly worked on video understanding until last year, and then we switched to doing more generative stuff. And I think one thing that I've been quite excited to see is how these two fields have been coming together. We know DALL-E 3 leverages like these captioning models to generate a lot of synthetic data. And I think, so yeah, basically like these video understanding models coming into play in building better video generation models, and potentially vice versa. I think that sort of confluence of those two fields is very exciting, and I hope to see a lot more of that going forward.
Okay, I think people can't hear very well. Yeah, that's right. This mic works, right? Yep. Okay, so we're going to try and pass this mic around instead. It's just, yeah, I think it just about reaches. I will shout. I can shout. Okay. Rich Sutton's bitter lesson is that compute and scaling beat hand coding special purpose knowledge for AI. But we know that data are critical too. And right now, sometimes we use special purpose data. So how do you see data in Gen AI, and how do you see it changing over time?
Yeah, of course, data is like one of the main ingredients to have like this scaling laws working. So for the pre-training, we definitely want a lot of data. Kind of all the data that you can get, and a lot of interesting stuff is I think happening in multimodal training, with the GPT-4 stuff and similar things. But then on the other hand, after the pre-training, you typically switch to this post-training mode where, yeah, Emu did like really nice work on showing that you just need a few really nice samples to align the model with an aesthetic preference. Another method to do that is to use ranked data, which is basically simplest way to do it is to just separate it into bad examples and good examples, and can do stuff like reference optimization. This also doesn't need a lot of data; it just needs high quality data. So there seems to be this this way of that the model is generating a little bit too much. It's a bit too diverse, and in the end, you actually want to align it with what you actually want. And for that, this specialized data seems to be very important.
I cannot agree more about the quality of the data. I think that at the beginning of the Firefly project, we were thinking, wow, there's so much data out there, including Lion and Clio. How do we differentiate ourselves? Should we just do the same as other models are doing, train on all the data that we can find? And hopefully our architecture design and our scaling will do better than other models. We tried a little bit, and we actually also accidentally trained on just our in-house data, Adobe Stock, which is comprised of only licensed data with no copyright content, no living artist contents. It's definitely at a scale smaller than the in the wild internet data, but we actually found that through careful data algorithm, data filtering, and data augmentation, we can actually, our model can actually generate better technical quality compared to models that are naively trained on just other data that you can find. Like by technical quality, I mean like sharpness, details, and even aesthetics, because our in-house data set is actually quite high quality, similar to Shutterstock and Getty. So actually that really means the data, not just quantity, but also the quality is very, very important. So Firefly image model released 3 versions of it until now. From the first version to the second version, actually, we changed the architecture, but we also added a lot more data that we specially sourced from other sources who actually own the copyright. And we actually found that the architecture and the data improvement actually significantly improved the quality of our generated images from Firefly Image 1 to Image 2. So yeah, so I think data quantity definitely very important, but quality is the key. And I would encourage people to spend more time doing data filtering.
Yeah, I agree. I think specifically talking about videos, one thing we realized working on Emu Video was how hard it is to find good quality video data. A lot of even the stock videos that you could access, they're often not really videos, they're very staticky. And this was one of our biggest like issues that we faced during Emu Video, and that's where like this last stage of fine-tuning and like fine-tuning on really high quality fast motion videos really made all the difference in actually making the model generate motion. So I think, yeah, getting good data is incredibly important, maybe even more important than the model scaling and so on. The other aspect that I'm quite excited about going forward, and I mean, I don't know if it'll work out or not with like from a research perspective, I'm really very excited about synthetic data. So one kind of synthetic data is just the one you could generate using a vision language model and so on, but also just synthetically generated pixels, like things out of a physics engine and things like that. And sort of my thinking there is similar to how LLMs have shown really good reasoning performance when being trained on code. I wonder if when you train these models on a lot of physics simulation and things like that, like maybe these models get better at like object permanence and other sort of visual reasoning tasks. So yeah, looking forward to how the data evolves in this space.
Research and industry can provide new data-driven tools to aid creators, but these can also have a negative impact upon existing creators and their work. For instance, making it easy to copy an artist's unique style easily. How should we as researchers respond to this impact?
Yeah, that's a really difficult question.
I think there's different approaches to the issue. I think Adobe is doing this training exclusively on their own data, and I'm not sure if there is a royalty share or not. But one approach is just to, for each generation, divided by the number of images in there, and then everyone just gets a little piece. This doesn't seem to be like very effective, and I think at least the royalty share thing, because it's just very tiny amounts, and we don't actually know which work was used for a particular generation. So I think where research could do something is actually look into this. One approach which we tried in the past was doing retrieval augmentation. So the model actually at inference time receives data from a data bank. That could be one of these data banks where you just have like your in-house data or from certain artists or whatever, and then you can really know that this part of the work has been used in the generation process. It's not a complete solution because it's only part of the generation. Obviously, you shouldn't copy the whole thing. It's just useless. And add interesting detail to it. Where this is coming from is then like, yes, it's just another question. But I think it might be one approach to at least get to something that is better than just this even non-informed distribution. And yeah, I think that's what I want to say.
So to answer your question, actually, we do compensate the contributors to Adobe stock. Right now in a very simple algorithm, but I agree that if there's a better, more intelligent way to figure out the relative importance of different images and videos that contribute to the generation of the images, and we pay based on the actual importance of the training data, I think that will be more scientific. And the good news is Adobe Research, my colleague Richard Zhang actually does have a line of research in this space. I think try to analyze data attribution based on for every generated image, try to find the training images that contribute to this generation the most. And I think that's just the start of a line of work, and it's very important work. I also want to mention that Adobe has spearheaded a new effort called Content Authenticity Initiative, which is not really new. It started in 2019, so it's been a couple of years. And it's a global coalition of industry open standard of trying to tackle the problem of digital content provenance. So what it does is to try to attach a content credential to every digital content that is generated and touched by various softwares that are within this coalition. So it tried to track when and where, by whom and how is a piece of digital content created. And then when it goes to the various platforms and software being edited, it will also optionally keep track of what kind of edit has been applied, and all Adobe products actually will allow you to attach this edit history to this content credential. It's kind of like a nutrition label for food. It's the nutrition label for digital content, and trying to really restore some trust and transparency about digital content. And the reason I'm mentioning this is that, and actually like 2,000 companies has joined this coalition already, including some of the prominent one, including Google, OpenAI, Meta. And the reason I'm mentioning this is I think there's a role for research to play in here as well.
In just a second.
Okay.
The microphone has done that thing where it stops for 30 seconds.
I certainly cannot project my voice.
Yeah. Seriously, we just have to wait.
Okay, try again.
Okay. Can people hear me now? The reason I'm mentioning this is that there are some research needed to study like watermarking, to study how to attach this content credential, this kind of nutrition label in a robust way that can go through the various social networks and platforms and be not that easily strippable or modifiable. So these kind of technology, I think, will really help this data provenance type of work.
So I totally agree with the approaches that Robin and Cynthia mentioned. I think ultimately we need a way of some sort of credit assignment. Like when you generate an image, what images potentially were used in or leveraged in generating these in some way. And yeah, there is a lot of work from Adobe, like Junyan Zhu and Richard Zhang, which takes some steps towards getting there. And I think that could be one way to fairly compensate creators when their artifacts derived from their work are being used in any of these tools. I guess the other thing that we should also be concerned about is artists who may not want their data to be inside your generative model, and they just want to opt out from that. And usually that's a tall order because these models are so big, you can't just delete that data and retrain it. So we need approaches which can potentially remove that data from a trained model, or not generate like that specific cat or a specific artifact that is owned by a certain artist. And I think to that end also there are some works, in fact something at CVPR, again I think from folks at Adobe and CMU and so on, I guess like concept ablation and so on. So basically approaches where you can like remove certain artifacts or certain concepts from your model, so it does not generate things that might infringe on a creator's copyright.
Okay, at this point, I want your best questions. Okay, but to try and be fair, I'll give you a number when you put your hand up, and then we'll go in order. Okay. Okay, we have 3. So 1, 2, 3. Please. It will come.
Yeah. You all seem like you're mostly from like a researchy world. Question is, when you're doing your work in this space, a lot of the work is sort of protected or has freedoms to use data that normally aren't available to the product side of the companies that you work for. And I'm interested in what your own personal experience is in like crossing that gap. Like you can use pretty wide range of data when you're in research, but what do you have to do to get it across the product where suddenly it's like a very different scenario for all the obvious reasons? Like how much of a challenge is it for you in your day-to-day, and what do you see as like good ways to make that like jump?
Repeat the question.
Okay. I guess if I hear you correctly, during research, all type of data can be used, and then how do we cross the line of moving the approach to product when we need to be more careful about the data that we use? Yeah. Yeah, so for Adobe, we have a lot of research that are done in the wild data set. And we actually, learn from, Stable Diffusion and learn from the research built on top of other open source data sets, and then to really validate certain approaches. And then when it comes to Firefly shipping, we actually, I used to come from a research organization, and I am in this more applied organization working on productization of Gen AI foundational models and applications. And I work really closely with the research team, trying to adopt mature techniques that they have verified on open source models, open source data into our in-house proprietary model using our proprietary data. So we definitely are very careful to make sure that our shipping products are using the data in an ethical and responsible way.
So actually for us at Meta, we are very careful about, basically don't have this separation as such. Even for like purely research work, we are very careful about like, following all the legal and policy guidelines in terms of the data we use. And I think this has been a kind of a switch since, research in the space has moved from being like one-off papers to things that like can quickly be deployed into products and are, deployed via demos and so on. So we actually don't even have that distinction anymore. We pretty much follow the same policies, even for a model that will only be used for, research publications.
And please be loud. So a lot of people now are just working on their own generative models for video or image, and everybody's starting doing the same thing. So how do you avoid getting bored working on generative models?
I mean, people like Robin and Cynthia don't let us get bored quickly.
Well, you certainly didn't like us get bored. It's not boring at all. There's so much to learn, so much to work on. Last night I was like answering the email from our CEO. So how is it going with the video model? I saw the Luma AI model is super cool after Sora. And then this morning I woke up to Runway Gen 3. Very exciting space. It's just a lot to read and learn. And I also see the convergence of multimodal, right? I think it's not boring that once video generation become a commodity like image generation to some extent, we will move into the more exciting world. But I also do want to mention from a more product perspective, I don't think that is done for image generation, right? Like at Adobe, we deeply understand the needs of the users. And actually, if you look at the details, if you look at the level of controls that existing model allow, it's not good enough for professional users. And we actually pay a lot of attention to the aspects that research community might not pay enough attention to, such as the resolution, such as speed. Robin was giving a really great call out about, working on distillation, and also just control, really direct, fine-grained vision controls. That is still lacking, right? Like there's a lot of dialogue-based interface, but really if you ask artists, they want all kinds of controls, especially direct visual controls. And how to balance following the control while still have the model to be creative and easy to use. That's a very interesting research questions. So it's definitely not boring.
Yeah, absolutely. Sometimes you wish it would be a bit more boring, I think, but there's so much to do. Like for video generation, you have to, like right now, it's about developing better video generation methods. Then they're lacking a lot of control right now. So that's something that would be of immediate use, I think. Then there is speeding up these video generators. They're so expensive to run. There's really so much stuff to do, I think. And then the other thing that typically happens is you have like kind of a leap. You train a new model that's larger and produces nice outputs. And then you have this wow effect. It's like, oh wow, it's really nice samples. And then you quickly get used to it. And I think the samples that we see right now from like stuff like Sora or other models, they are impressive, but then it's, I don't know, you get used to it, and then I think in a few years you will think like this is like super low quality stuff. So yeah, I think there's enough to do.
Well, I noticed that the field of generative AI is evolving very fast, and after for example, specifically in video generation, after the quality is good enough, the resolution is high enough, and we can generate long enough video. What kind of capabilities do you think are the future directions? Like after getting these very strong foundation video generation models, what will be the next step that the industry should be most focusing on?
So the question was, what for large-scale video foundation models are, once we have them, what are the next immediate steps that research should focus on? Is that right? I think one of them, which I'm super excited about, is something called character consistency. That's just one application where, let's say you have a text-to-video model. then you want to be able to not only prompt it with a text, but I don't know, an image of yourself, an identity of yourself, any other object or something like that. You want to be able to insert that into different contexts. This seems to me like a super exciting application, but that's just one example. I guess you have more.
So for me, the most compelling use case for video generation would be generating how-to videos. And I see some of my colleagues who work with me on Emo Video are here, and they might remember me talking about it. But the thing that I really wanted to generate with a good video generation model was basically like, cooking recipe videos, because that's what I mostly consume on YouTube. And that's pretty much how I've learned how to cook. And it will be so great to be able to generate any like a recipe video in the style of your favorite creator or for whatever specific bespoke recipe you want, and change whatever ingredients that you don't like or whatever equipment you have and don't have, and be able to construct that sort of bespoke video that's specifically for your specific situation, and that teaches you how to do things. And cooking is just one example. It could be like fixing your sink, or changing a tire and things like that.
I guess I can add that in the video space, right? I'm not sure how many works are looking into generating video and audio together in a synchronized way, right? I think the challenge there is probably the lack of data that allow you, lack of large scale data that allow you to do this generation, and maybe smart algorithms that allow you to train unsynchronized video and audio data, but still allow you to do such generation might be very interesting. I also think that just in general, as I think some of you pointed out, that this space actually scaling is the key, but only a few companies can really afford scaling the model and equivalently scaling the data. So really more research into like small efficient model that is also data efficient, right? To allow other startups and academias and build specialized small models fit specific needs is also an interesting direction, because I don't think all the companies and university can afford doing research in this space. And also it's just not very eco-friendly to deploy large model for any type of use cases. And for some use cases, maybe a specialized small model will be good enough. So how to do that, I think, is also an interesting direction.
Okay, we have more hands. Let's see. 1, 2, 3. Please. Sorry, behind. Sorry, it was a gentleman behind.
Oh,
sorry. Please project. Please be loud.
Oh, okay. Yeah. So yeah, thanks for answering all the sharing your opinions. So yeah, I'm wondering. So yeah, for example, when you're working working on the large scale models with the large scale data set, so usually we need a team to work on such kinds of things. So what do you think about the team flow or the team preparation on such kind of works? Because sometimes when we discuss with some of my friends, they just told me that for researchers, for example, they are more willing to train models instead of like doing the data processing, some kinds of work. So yeah, so for such kinds of things, do you have any suggestions for this? And also so maybe a more technical one.
Can we just do one question at a time? Thanks. Okay. Let's take the question about teams. So the question was, how do you work as a team on this area?
Yeah, that's super relevant question, and I think if you really want to go into scaling these models, it's something that you just have to do. It's a bit of a pain because one thing that you realize is that it needs heavy data preprocessing. We wrote a little bit about this in this C3 paper. You typically, if you also want to experiment on your data, train different models, you want to pre-calculate all the embeddings that you have, then you need to have like dedicated data loading pipelines for this. having data loading for video at scale is kind of difficult. I guess you can also talk about this. And that definitely needs a team effort. So this is where you cannot really do it like as an individual. I think like training like a model, like, I don't know, small text image model that is still feasible to do alone. It's probably not the most efficient way to do it, but that's something you can do. But then going into anything larger and doing multiple studies is just possible if you really accept the fact that you have to do a lot of pre-processing and yeah, then have different subgroups in your team to actually do that. The same is also true for not only for pre-processing but also for post-training, right? So with some guys doing pre-training, then others are very specialized in post-training, DPO training and stuff like this. I think that's super important. Otherwise, it's super hard to compete.
Yeah, totally agree with that. And in fact, like I think all members of the team have to develop some of those skills because all these aspects are kind of related. So like I have worked on data filtering, model scaling, and the things I've learned about model parallel. I don't expect I will be learning, but I think that's just super important. You just cannot even like do inference with some of these models without going to like some sort of like model parallelism and things like that. So I think, yeah, those are skills that all of us need to learn. And in general, the team needs to have some of that expertise, some folks who can like really help you debug and unblock nickel errors because, the CUDA version on one of your nodes is different or whatever. So yeah, you need that sort of mix of skills to be able to really train these models.
I think it's really a mindset change from working in university to going to industry, right? Just to recognize that, like a lot of people are saying, right, the data, the scaling are key, right? So working on data algorithms, efficient data streaming, data infrastructure, as well as system level optimization of the training efficiency are perhaps the most important things compared to architecture, which is just a really small part of a whole team. And I definitely don't recommend one person doing all of these. When the project started, we had one person who's sitting in this room who trained all the models, keeping all the compute occupied, very stressful, can't take vacations. I don't recommend doing that. It's a very big team effort to get to where we are right now.
The question was more about how do we encourage researchers to do more dirty data work? I think.
Yeah, I think it's just if you, as a researcher, want to arrive at a model that is somewhat competitive, then you have to, there's no way around this. You have to do it. You have to learn, I don't know, read the Zero paper, which introduces like optimized sharding, gradient sharding, all these kind of techniques. They're super important. And you typically don't need them during a PhD. But it's something that is just like, you want to go beyond 2-point-something billion parameters in your model, and you need to do it. And yeah, that's otherwise you just have to do some other research.
CVPR has a data sets track, so you should go to those talks.
Thanks. So a technical question. Building off what Cynthia said about multimodals and Robin's, the title of Robin's talk about diffusion, do you think that there's an inherent problem with integrating stuff from other modalities, which usually is like autoregressive transformers, and there are lots of very, very interesting advances that were made there, with using diffusion, because diffusion introduces noisy tokens and lots of things can't be done because of that. Do you think that this is an inherent problem, or that there's a way around it?
Yeah, I think there's two different angles to this. One, let's say we just want to use a very large pre-trained language model like Llama 3 as a better text encoder than a completely outdated T5, which is I think 5 years old or 4, and is still present in most of the text to image and text to video models, which is weird. So one thing that people are looking into is using autoregressive models for producing text embeddings. But since these models work a bit differently, it's not that straightforward. I do think that we will see this more and more in the future. But yeah, since you basically these models, they receive text tokens as an input, they produce text tokens as an output. So the best representation might be somewhere in the middle. It might actually be entangled over different layers. So there's some research to be done there, but I guess something we will see soon. The other aspect to this, which I found super interesting, is actually comparing autoregressive models and diffusion models in terms of training efficiency. Autoregressive models are much more training efficient than diffusion models. For autoregressive models, you typically, what you can do is you construct a training target by just shifting the sequence by one, and then you predict all the token transition probabilities at the same time for a given example, which is a super dense training signal. For diffusion model, you only sample a single time step and try to denoise that, which is very, very sparse in comparison. And I think this is something where we might see some maybe even changes from like maybe going back to autoregression in this domain or combining it with diffusion. The other aspect is actually inference. There's a lot of research going into optimizing large language models. There's even hardware being built around it. So that could be another thing where we, which could drive us back into autoregression. And then one more advantage that's also on the autoregressive side is that you typically cache your activations and then only predict those for the next token. In diffusion models, you always have to operate on the full sequence. So it seems pretty inefficient actually. Diffusion models have these nice features that they enable editing, zero-shot interpolation, zero-shot if you think about videos. The quality is higher for using autoregressive models. You would have to improve tokenization quite significantly to achieve the same level of quality. But yeah, obviously there's a lot of stuff to do actually.
Everybody is talking about scaling, and however, there will be big waste of resource if we start in big scaling from the beginning. So, and even in universities, it is very difficult to acquire those big resources. So, before working on your large models, do you start from small versions of your models and small data set? And if yes, could you provide some tips or guesses that will be helpful for designing small experiments?
So yeah, basically we do start with smaller models. So for example, you can take the llama example. We have all the way up to 4 or 5B, but we usually do a lot of experiments at 7B. I should say though that a lot of the things you see at larger scales, you often do not see them at smaller scales. So even though you get some signal on what works, what doesn't work, it may not be like a very reliable signal, and ultimately you still end up doing a few experiments at that large scale to actually figure out like what hyperparameters work the best and like what data mix works the best and so on. But it does keep like the smaller scale models do give you some signal.
Yeah, we do experiment on smaller scale model as well. And sometimes also subsetting our data set to a smaller subset to try to understand specific aspect that we want to understand. But I agree that some of the behaviors you simply just won't observe until you train it at a full scale and train it for long enough. So it's definitely that itself, how to scientifically design the sequence of experiments to go from small scale to large scale. To be honest, I think it's still like science, it's still research to figure out how do we do that. Yeah.
Yeah, maybe one little thing to add there is that you run into problems when you try to scale up the models. So you run into training instabilities and stuff like this. This is something that you can't really. It's kind of hard to predict. And yeah, I think you said that there's kind of a research on its own, and it's kind of difficult to do it at low scale because then these phenomena like divergence might just not happen.
Basically, there are two key components in image generation. The first one is image tokenizer, and the second one is the diffusion. So my question, sorry, for the first question, compared to large language model, the image tokenizer seems to hard to compress data. For example, large language model can compress hundreds of TB data into several billion parameters, but for image tokenizer, it seems still hard to achieve it. And my second question.
One question. Can we just do
Okay,
one question?
that's my question. Yes. So, do you think the image tokenizer is a bottleneck for image generation instead of just data?
Please repeat the question as you understand.
The question was, if I understand correctly, is the image tokenizer a bottleneck for the image generation quality?
Since it cannot achieve similar compression ratio as text or large language model.
I'm actually not sure if I agree. Like, images are much more compressible than text. I think that's just the key insight why stuff like, yeah, like diffusion or other types of tokenization work. And language is such a dense representation that you don't really train an oracle on top of it to compress it further. But you're right in a way that the quality of your image tokenizer or video tokenizer outperforms the quality that you can achieve with a diffusion model or autoregressive transformer that you train in that latent space. So you cannot go beyond that. If you have certain effects in your tokenizer, you will have them all the time. It's something that diffusion model cannot solve them for you. So that's right, yeah.
Yeah, I think Robin pretty much answered that. And I do think I think images are pretty compressible. Like if you look at the amount of like raw data versus like a VQGAN that you train on, it's like much smaller in representation space. So yeah, I think they're pretty compressible.
Since this topic is like Gen AI industry, you're all in the as a researchers in industry. I'm wondering like whether in the past of experience have you faced like a pressure production or basically like production team like have like some need have some OKR metrics to measure like your success. Nowadays, like especially after Stable Diffusion and the Sora, maybe the leadership maybe already believe this direction is right way to go, just invest more money and human into this area. In the past, like since this Gen AI just recently 2 or 3 years thing, so have you like facing this kind of challenge? Even know that's a good news for you, maybe. But like if yes, can you share some like learning suggestion on that topic? Not sure whether this question makes sense. Yeah. Okay.
Please repeat it. Yeah, the question is about whether we have faced pressure from the leadership, I guess, because of the success of Gen AI. And so yeah, I think yes, and I wouldn't say it's necessarily a bad thing. To some extent, it also validates our work and provides a lot more support that we maybe previously didn't have in terms of resources, unblocking a lot of processes. So overall, I think it's been a positive, and yeah, I mean, of course, that does bring with it some constraints on, things that you can and cannot do. You maybe cannot try like, super crazy stuff and especially when you're, dealing with such large compute clusters, like as Robin was saying, like sometimes these models just diverge. So you can't really try a crazy thing at like, when you're training something on like, I don't know, 2000 GPUs. You probably want to go with something that's much more tried and tested, or things that are sort of popular in literature. So given that constraint, other than that, like I think you have a lot of support and resources, so that I think is a positive.
I can say that one of the consistent pressures that I have is that there are so many Adobe products that are welcoming Gen AI features. And how do we prioritize what features to build for what particular quality metrics is a prioritization headache. And also one thing that I have always been trying to communicate, which is very easy to understand for academics and researchers, but very hard to understand for business executives, is that these kind of applied research and prioritization efforts are very highly unpredictable. Right, just like Rohit mentioned, that sometimes you, out of no reason, that maybe your model diverge and then collapse or whatever reason. And there's still a lot of it that we don't quite understand, right? Really trying to understand the model behavior, why certain things happens. I think there's more research to be done. And so I have always been needing to communicate that these things are unpredictable, and we want to give researchers, applied researchers, more time to really get things to work and not rushing into a particular predefined timeline. But definitely there are, it's very exciting space, and other products wants to leverage them to bring more users and keep existing users on the platform. So it's understandable that there will be shipping pressure.
Maybe a tiny perspective to add to that is that actually there was a shift in how the workflow or the direction of information flow is going. So in the past, when you were working on text image generation or text video, it was kind of very experimental, right? And then that changed quite rapidly. So in the past, you could just develop that. It was kind of an academic project. Nobody really cared about it. Now you have user demands, if you want to say that. So actually, the research is driven by, we need to change this and this in the model to add this certain functionality. And this is kind of, something that you have to get used to, I think, because as a researcher, because it's just a different mindset, because you cannot just throw a model out there and then hope that it will be picked up in some way. There's some real demand now, and certain features are just needed.
All right, we're running a little out of time. So I will just ask one more final question. We have lots of people in the room who might be budding Gen AI engineers or Gen AI researchers. So within your teams, let's say, what's one critical skill that helps people to be effective in Gen AI?
I think it's not so much about being effective, but more about being creative. Because if you look at what you can squeeze out of pre-trained models with very simple tricks, like there was this recent paper by NVIDIA on guiding a model with a bad version of itself, which works extremely well. And that's just like something that you can just try, because you usually have like all the checkpoints lying around. And this kind of stuff, it's also other work and improving the guidance and just the post-training inference. So yeah, you need to have some desire to play with the models, to hack stuff, and then you can arrive at these solutions that give you much better outputs actually.
I will add that other than creativity, I think a lot of people pursuing PhD doing research have that, which is great. But the other really important thing that is very important for Gen AI, large-scale production model training, is engineering, right? Really need to be a engineer at heart and care about teamwork, because it's always a big teamwork, and write modularized code and documentation, and care about system level optimization, because if you cannot scale, your special designed architecture might not work. So I think that as well as communication, right? Working in a big team, being able to effectively communicate through code, through presentation and documentation is very important in the industry environment.
Follow-up question.
Sorry, can we just let Rohit respond? Thanks.
Actually, I totally agree with the 2 points being raised, and that's basically what I was going to say as well. I mean, papers like visual anagrams, and they're so interesting, and they just pop out of a pre-trained model. And at the same time, like scaling has been one of the most important things that I've seen. Like a lot of our big models are largely trained, with folks who are really experienced in dealing with a lot of like system level issues, and like you almost need a new level of debugging scale to figure out, when you have these large clusters, like how do you even figure out like why a certain node is failing? You literally look at like the number of lines of logs each worker is writing, and so that sort of skill is something that would be great to develop.
Let's take that offline, sorry. We are out of time. Thank you very much for your questions. Let's thank our panelists for doing. Okay, we are done for this room. We have one more poster session. So those of you, yeah, we can have a round of applause. Thanks, everybody.
I don't know, this was about this
Okay. 4E.
Do you want one?
To see your posters.
I think I'll just.
Otherwise, thanks very much. See you next year.
I'll see you Wednesday.
I see. Are you going to do dinner later?
I already have another party to go to. I might stop by. But actually, where is the dinner?